Chapter 5 Junctions Objectives 1. Determine the band diagram of a p-n junction in equilibrium and use the Poisson's equation to calculate electric fields and potentials. 2. Determine current flow components in an ideal diode, and why reverse leakage in an ideal diode is independent of bias. Study applications in rectifiers. 3. Understand depletion capacitance due to dopant charges, and diffusion capacitance due to mobile carriers. 4. Study second-order effects: high-level injection, generation recombination in depletion region, series resistance, and graded junctions. 5. Study metal semiconductor junctions, Schottky and ohmic, and heterojunctions, in terms of vacuum level, electron affinity, and work function. Most semiconductor devices contain at least one junction between p-type and n-type material. These p-n junctions are fundamental to the performance of functions such as rectification, amplification, switching, and other operations in electronic circuits. In this chapter we shall discuss the equilibrium state of the junction and the flow of electrons and holes across a junction under steady state and transient conditions. This is followed by a discussion of metal semiconductor junctions and heterojunctions between semiconductors having different band gaps. With the background provided in this chapter on junction properties, we can then discuss specific devices in later chapters. Although this book deals primarily with how devices work rather than how they are made, it is instructive to have an overview of the fabrication process in order to appreciate device physics. We have already discussed in Chapter 1 how single crystal substrates and epitaxial layers needed for high-quality devices are grown, and how the doping can be varied as a function of depth. However, we have not discussed how doping can be varied laterally across the surface, which is key to making integrated circuits on a wafer. Hence, it is necessary to be able to form patterned masks on the wafer corresponding to the circuitry, and introduce the dopants selectively through windows in the mask. We will first briefly describe the major process steps that form the underpinnings of modern integrated circuit manufacturing. Relatively few unit process steps can be used in different permutations and combinations to make everything from simple diodes to the most complex microprocessors. Thermal oxidation. Many fabrication steps involve heating up the wafer in order to enhance a chemical process. An important example of this is thermal oxidation of silicon to form silicon dioxide. This involves placing a batch of wafers in a clean silica, quartz, tube which can be heated to very high temperatures, 800, 1000 degrees C, using heating coils in a furnace with ceramic brick insulating liners. An oxygen-containing gas such as dry oxygen or water is flowed into the tube at atmospheric pressure, and flowed out at the other end. Traditionally, horizontal furnaces were used, Fig 5.1a. More recently, it has become common to employ vertical furnaces, Fig 5.1b. A batch of silicon wafers is placed in the silica wafer holders, each facing down to minimize particulate contamination. The wafers are then moved into the furnace. The gases flow in from the top and flow out at the bottom, providing more uniform flow than in conventional horizontal furnaces. The overall reactions that occur during oxidation are Si plus O2 SSiO2, dry oxidation. Si plus 2H2O SSiO2 plus 2H2, wet oxidation. In both cases, silicon is consumed from the surface of the substrate. For every micron of silicon dioxide grown, 0.44 micrometers of silicon is consumed, leading to a 2,2 volume expansion of the consumed layer upon oxidation. Figure 5.1 A silicon wafers being loaded into a furnace. For 8-inch and larger wafers, this type of horizontal loading is often replaced by a vertical furnace. Figure 5.1b Vertical furnace for large silicon wafers. The silica wafer holder is loaded with silicon wafers and moved into the furnace above for oxidation, diffusion, or deposition operations. The oxidation proceeds by having the oxidant, oxygen or water, molecules diffuse through the already grown oxide to the silicon-silicon dioxide interface, where the above reactions take place. One of the very important reasons why silicon integrated circuits exist, and by extension why modern computers exist, is that a stable thermal oxide can be grown on silicon with excellent interface electrical properties. Other semiconductor materials do not have such a useful native oxide. We can argue that modern electronics and computer technology owe their existence to this simple oxidation process. Plots of oxide thickness as a function of time, at different temperatures, are shown for dry and wet oxidation of 100 silicon in Appendix 4. Diffusion. Another thermal process that was used extensively in IC fabrication in the past is thermal indiffusion of dopants in furnaces such as those shown in Fig 5.1a. The wafers are first oxidized and windows are opened in the oxide. Using the photolithography and etching steps described in sections 5.1.6 and 5.1.7, respectively. Dopants such as boron, phosphor, or arsine are introduced into these patterned wafers in a high temperature, 800 to 1100 degrees Celsius, diffusion furnace. Generally using a gas or vapor source. The dopants are gradually transported from the high concentration region near the surface into the substrate through diffusion, similar to that described for carriers in section 4.4. The maximum number of impurities that can be dissolved, the solid solubility, in silicon is shown for various impurities as a function of temperature in Appendix 7. The diffusivity of dopants in solids, D, has a strong Arrhenius dependence on temperature, T. It is given by D equal D0 exp, Ea caret, where D0 is a constant depending on the material and the dopant, and Ea is the activation energy. The average distance the dopants diffuse is related to the diffusion length as in section 4.4.4. In this case, the diffusion length is 2 dt, where t is the processing time. The product dt is sometimes called the thermal budget. The Arrhenius dependence of diffusivity on temperature explains why high temperatures are required for diffusion, otherwise, the diffusivities are far too low. Since d varies exponentially with t, it is critical to have very precise control over the furnace temperatures, within several degrees, in order to have control over the diffusion profiles, Fig 5.2. The dopants are effectively blocked or masked by the oxide because their diffusivity in oxide is very low. The diffusivities of various dopants in silicon and silicon dioxide are shown as a function of temperature in Appendix 8. Difficulty with profile control and the very high temperature requirement has led to diffusion being supplanted by ion implantation as a doping technique, as discussed in section 5.1.4. The trend of using larger silicon wafers has changed many processing steps. For example, 8-inch and larger wafers are best handled in a vertical furnace, Fig 5.1b, rather than the traditional horizontal furnace, Fig 5.1a. Also, large wafers are often handled individually for a variety of deposition, etching, and implantation processes. Such single wafer processing has led to development of robotic systems for fast and accurate wafer handling. The distribution of impurities in the sample at any time during the diffusion can be calculated from a solution of the diffusion equation with appropriate boundary conditions. If the source of dopant atoms at the surface of the sample is limited, for example, a given number of atoms deposited on the silicon surface before diffusion, a Gaussian distribution as described by EQ 444, 4x70, is obtained. Figure 5.2 Impurity concentration profile for fabricating a p-n junction by diffusion. On the other hand, if the dopant atoms are supplied continuously, such that the concentration at the surface is maintained at a constant value, the distribution follows what is called a complementary error function. In Fig 5.2, there is some point in the sample at which the introduced acceptor concentration just equals the background donor concentration in the originally n-type sample. This point is the location of the p-n junction. To the left of this point in the sample of Fig 5.2, acceptor atoms predominate and the material is p-type, whereas to the right of the junction, the background donor atoms predominate and the material is n-type. The depth of the junction beneath the surface of the sample can be controlled by the time and temperature of the diffusion, Prob 5.2. In the horizontal diffusion furnace shown in Fig 5.1a, silicon wafers are placed in the tube during diffusion, and the impurity atoms are introduced into the gas which flows through the silica tube. Common impurity source materials for diffusions in silicon are boron oxide, boron bromide, and boron chloride. For boron, phosphorus sources include phosphor hydride, phosphor oxide, and phosphor oxide chloride. Solid sources are placed in the silica tube upstream from the sample or in a separate heating zone of the furnace. Gaseous sources can be metered directly into the gas flow system, and with liquid sources inert carrier gas is bubbled through the liquid before being introduced into the furnace tube. The silicon wafers are held in a silica boat, Fig 5.1a, which can be pushed into position in the furnace and removed by a silica rod. It is important to remember the degree of cleanliness required in these processing steps. Since typical doping concentrations represent 1 part per million or less, cleanliness and purity of materials are critically important. Thus the impurity source and carrier gas must be extremely pure, the silica tube, sample holder, and push rod must be cleaned and etched in hydrofluoric acid, HF, before use. Once in use, the tube cleanliness can be maintained if no unwanted impurities are introduced. Finally, the Si wafers themselves must undergo an elaborate cleaning procedure before diffusion, including a final etch containing hydrofluoric acid to remove any unwanted silicon dioxide from the surface. Rapid thermal processing. Increasingly, many thermal steps formerly performed in furnaces are being done using what is called rapid thermal processing, RTP. This includes rapid thermal oxidation, annealing of ion implantation, and chemical vapor deposition, which are discussed in the following paragraphs. A simple rapid thermal processing system is shown in Fig 5.3. Instead of having a large batch of wafers in a conventional furnace where the temperature cannot be changed rapidly, a single wafer is held, face down to minimize particulates, on low thermal mass quartz pins, surrounded by a bank of high-intensity, tens of kilowatts, tungsten halogen infrared lamps, with gold-plated reflectors around them. By turning on the lamps, the high-intensity infrared radiation shines through the quartz chamber and is absorbed by the wafer, causing its temperature to rise very rapidly, 50 to 100 degrees Celsius S. The processing temperature can be reached quickly, after the gas flows have been stabilized in the chamber. Figure 5.3 Schematic diagram of a rapid thermal processor and typical time temperature profile. At the end of the process, the lamps are turned off, allowing the wafer temperature to drop rapidly, once again because of the much lower thermal mass of an rapid thermal processing system compared to a furnace. In rapid thermal processing, therefore, temperature is essentially used as a switch to start or quench the reaction. Two critical aspects of RTP are ensuring temperature uniformity across large wafers and accurate temperature measurement, for example, with thermocouples or pyrometers. A key parameter in all thermal processing steps is the thermal budget, dT. Generally speaking, we try to minimize this quantity because an excessive dT product leads to loss of control over compact doping profiles, which is detrimental to ultra-small devices. In furnace processing, thermal budgets are minimized by operating at as low a temperature as feasible so that D is small. On the other hand, RTP operates at higher temperatures, 1000 degrees Celsius, but does so for only a few seconds, compared to minutes or hours in a furnace. Ion implantation. A useful alternative to high-temperature diffusion is the direct implantation of energetic ions into the semiconductor. In this process a beam of impurity ions is accelerated to kinetic energies ranging from several kilo-electron-volts to several mega-electron-volts and is directed onto the surface of the semiconductor. As the impurity atoms enter the crystal, they give up their energy to the lattice in collisions and finally come to rest at some average penetration depth, called the projected range. Figure 5.4. Distributions of implanted impurities. Gaussian distribution of boron atoms about a projected range Rp. In this example, a dose of 100 trillion of boron atoms per square centimeter implanted at 140 kilo electron volts. Depending on the impurity and its implantation energy, the range in a given semiconductor may vary from a few hundred angstroms to about 1 ohm. For most implantations, the ions come to rest distributed almost evenly about the projected range Rp, as shown in Fig. 5.4. An implanted dose of H ions cm2 is distributed approximately by a Gaussian formula, where Rp, called the straggle, measures the half-width of the distribution at E12 of the peak, Fig. 5.4. Both Rp and Rp increase with increasing implantation energy. These parameters are shown as a function of energy for various implant species into silicon in Appendix 9. Figure 5.5 Schematic diagram of an ion implantation system. An ion implanter is shown schematically in Fig. 5.5. A gas containing the desired impurity is ionized within the source and is then extracted into the acceleration tube. After acceleration to the desired kinetic energy, the ions are passed through a mass separator to ensure that only the desired ion species enters the drift tube. The ion beam is then focused and scanned electrostatically over the surface of the wafer in the target chamber. Repetitive scanning in a raster pattern provides exceptionally uniform doping of the wafer surface. The target chamber commonly includes automatic wafer handling facilities to speed up the process of implanting many wafers per hour. An obvious advantage of implantation is that it can be done at relatively low temperatures. This means that doping layers can be implanted without disturbing previously diffused regions. The ions can be blocked by metal or photoresist layers. Therefore, the photolithographic techniques described in section 5.1.6 can be used to define ion-implanted doping patterns. Very shallow, tenths of a micron, and well-defined doping layers can be achieved by this method. As we shall see in later chapters, many devices require thin doping regions and may be improved by ion implantation techniques. Furthermore, it is possible to implant impurities which do not diffuse conveniently into semiconductors. One of the major advantages of implantation is the precise control of doping concentration it provides. Since the ion beam current can be measured accurately during implantation, a precise quantity of impurity can be introduced. This control over doping level, along with the uniformity of the implant over the wafer surface, make ion implantation particularly attractive for the fabrication of silicon integrated circuits, Chapter 9. One problem with this doping method is the lattice damage which results from collisions between the ions and the lattice atoms. However, most of this damage can be removed in silicon by heating the crystal after the implantation. This process is called annealing. Although silicon can be heated to temperatures in excess of 1000 degrees Celsius without difficulty, gallium arsenide and some other compounds tend to dissociate at high temperatures. For example, as evaporation from the surface of gallium arsenide during annealing damages the sample. Therefore, it is common to encapsulate the gallium arsenide with a thin layer of silicon nitride during the anneal. Another approach to annealing either Si or compounds is to heat the sample only briefly, for example, 10S, using rapid thermal processing, rather than a conventional furnace. Annealing leads to some unintended diffusion of the implanted species. It is desirable to minimize this diffusion by optimizing the annealing time and temperature. The profile after annealing is given by chemical vapor deposition, CVD. At various stages of device fabrication, thin films of dielectrics, semiconductors and metals have to be formed on the wafer and then patterned and etched. We have already discussed one important example of this involving thermal oxidation of silicon. Silicon dioxide films can also be formed by low pressure, 100 mTOR, 2 chemical vapor deposition, Fig. 5.6, or plasma-enhanced chemical vapor deposition. The key differences are that thermal oxidation consumes silicon from the substrate, and very high temperatures are required, whereas chemical vapor deposition of silicon dioxide does not consume silicon from the substrate and can be done at much lower temperatures. The chemical vapor deposition process reacts a silicon-containing gas such as silicon hydride with an oxygen-containing precursor, causing a chemical reaction, leading to the deposition of silicon dioxide on the substrate. Being able to deposit silicon dioxide is very important in certain applications. As a complicated device structure is built up, the Si substrate may not be available for reaction, or there may be metallization on the wafer that cannot withstand very high temperatures. In such cases, chemical vapor deposition is a necessary alternative. Although we have used deposition of silicon dioxide as an important example, low-pressure plasma-enhanced chemical vapor deposition is also widely used to deposit other dielectrics such as silicon nitride, Si3N4, and polycrystalline or amorphous silicon. It should also be clear that the vapor phase epitaxy of silicon or metal organic chemical vapor deposition of compound semiconductors discussed in Chapter 1 is really a special, more challenging example of chemical vapor deposition where not only must a film be deposited, but single crystal growth must also be maintained. Patterns corresponding to complex circuitry are formed on a wafer using photolithography. This involves first generating a reticle, which is a transparent silica, quartz, plate containing the pattern, Fig 5.7a. Opaque regions on the mask are made up of an ultraviolet, UV, light-absorbing layer, such as iron oxide. The reticle typically contains the patterns corresponding to a single chip or die, rather than the entire wafer, in which case it would be called a mask. It is usually created by a computer-controlled electron beam driven by the circuit layout data, using pattern generation software. A thin layer of electron beam sensitive material called electron beam resist is placed on the iron oxide covered quartz plate, and the resist is exposed by the electron beam. A resist is a thin organic polymer layer that undergoes chemical changes if it is exposed to energetic particles such as electrons or photons. The resist is exposed selectively, corresponding to the patterns that are required. After exposure, the resist is developed in a chemical solution. There are two types of resist. The developer is used to remove either the exposed, positive resist, or the unexposed, negative resist, material. The iron oxide layer is then selectively etched off in a plasma to generate the appropriate patterns. The reticle can be used repeatedly to pattern Si wafers. To make a typical integrated circuit, a dozen or more reticles are required, corresponding to different process steps. Figure 5.7a. A photolithographic reticle used for one step in the processing of a 16 MB dynamic random access memory. In a stepper projection exposure system, ultraviolet light shines through the glass plate and the image is projected onto the wafer to expose photoresist for one die in the array of circuits and then steps to the next. Photograph courtesy of IBM Corp. The silicon wafers are first covered with an ultraviolet light-sensitive organic material or photoemulsion called photoresist by dispensing the liquid resist onto the wafer and spinning it rapidly, 3000 rpm, to form a uniform coating, 0.5 ohm. As mentioned above, there are two types of resist: negative, which forms the opposite polarity image on the wafer compared to that on the reticle, and positive, same polarity. Currently, positive resist has supplanted negative because it can achieve far better resolution, down to 0.25 ohm using ultraviolet light. The light shines on the resist-covered wafer through the reticle, causing the exposed regions to become acidified. Subsequently, the exposed wafers are developed in a basic solution of sodium hydroxide, which causes the exposed resist to etch away. Thereby, the pattern on the reticle is transferred to the die on the wafer. After the remaining resist is cured by baking at 125 degrees Celsius in order to harden it, the appropriate process step can be performed, such as implanting dopants through windows in the resist pattern or plasma etching of the underlying layers. The exposure of the wafers is achieved die by die in a step and repeat system called a stepper, Fig 5.7b. As the name implies, the ultraviolet light shines selectively through the reticle onto a single die location. After the photo exposure is done, the wafer mechanically translates on a precisely controlled XY translation stage to the next die location and is exposed again. It is very important to be able to precisely align the patterns on the reticle with respect to pre-existing patterns on the wafer, which is why these tools are also sometimes known as mask aligners. An advantage of such a stepper projection system is that refocusing and realignment can be done at each die to accommodate slight variations in surface flatness across the wafer. This is especially important in printing ultra-small line widths over a very large wafer. The success of modern integrated circuit manufacture has depended on numerous advances in deep ultraviolet light sources, precision optical projection systems, techniques for registration between masking layers, and stepper design. What makes photolithography, along with etching, so critical is that it obviously determines how small and closely packed the individual devices, for example, transistors, can be made. We shall see that smaller devices operate better in terms of higher speed and lower power dissipation. What makes modern lithography so challenging is the fact that pattern dimensions are comparable to the wavelength of light that is used. Under these circumstances we cannot treat light propagation using simple geometrical ray optics, rather, the wave nature of light is manifested in terms of diffraction, which makes it harder to control the patterns. The diffraction-limited minimum geometry is given by where L is the wavelength of the light and Na, 0.5, is the numerical aperture or size of the lens used in the aligner. This expression implies that for finer patterns, we should work with larger, and, therefore, more expensive, lenses and shorter wavelengths. As a result, smaller geometries require shorter wavelengths. This has led the push to replace ultraviolet mercury lamp sources, 0.365 micrometers, shown in Fig 5.7b, with argon fluoride, ARF, excimer lasers, L equals 0.193 micrometers. Novel exposure techniques employing phase shift masks, optical proximity correction, and off-axis illumination all exploit Fourier optics to allow resolution near or below the dimension of the wavelength being used. There is also interest in extreme ultraviolet, EUV, sources, 13 nanometers, which use a plasma to generate such short wavelengths, for next-generation lithography. X-ray lithography involving even shorter wavelengths has been the source of much research for many years, but does not seem practical in a manufacturing environment. A promising advancement involves imprinting patterns in a photoresist using a physical pattern, or mold, thereby overcoming the diffraction limits of optical lithography. The other key parameter in lithography is the so-called depth of focus, which is given by the depth of focus tells us the range of distances around the focal plane where the image quality is sharp. Unfortunately, this expression implies that exposure with very short wavelengths leads to poor DOF. This is a big challenge, because the topography or the hills and valleys on a chip during processing can be larger than the DOF allowed by the optics. We must therefore add steps in the fabrication process to planarize the surface using chemical mechanical polishing, CMP. As the name implies, the planarizing process is partly chemical in nature, using a basic solution, and partly mechanical grinding of the layers using an abrasive slurry. As described in section 1.3.3, CMP can be achieved using a slurry of fine silicon dioxide particles in an sodium hydroxide solution. The expression for diffraction-limited geometry EQ 5.2a explains why there is interest in electron beam lithography. The de Broglie relation states that the wavelength of a particle varies inversely with its momentum. Thus, more massive or energetic particles have shorter wavelengths. Electron beams are easily generated, focused, and deflected. Since a 10 kilo electron-volt electron has a wavelength of about 0.1 angstrom, the line width limits become the size of the focused beam and its interaction with the photoresist layer. It is possible to achieve line widths of 0.1 mm by direct electron beam writing on the wafer photoresist. Furthermore, the computer-controlled electron beam exposure requires no masks. This capability allows extremely dense packing of circuit elements on the chip, but direct writing of complex patterns is slow. Because of the time required for electron beam wafer exposure, it is usually advantageous to use electron beam writing to make the reticle, Fig 5.7a, and then to expose the wafer photoresist by using photons. Another approach being considered is electron projection lithography, using a mask, instead of steering a focused electron beam, in order to solve the throughput problem. Etching. After the photoresist pattern is formed, it can be used as a mask to etch the material underneath. In the early days of silicon technology, etching was done using wet chemicals. For example, dilute hydrofluoric acid can be used to etch silicon dioxide layers grown on a silicon substrate with excellent selectivity. The term selectivity here refers to the fact that hydrofluoric acid attacks silicon dioxide, but does not affect the silicon substrate underneath or the photoresist mask. Although many wet etches are selective, they are unfortunately isotropic, which means that they etch as fast laterally as they etch vertically. This is unacceptable for ultra-small features. Hence, wet etching has been largely supplanted by dry, plasma-based etching, which can be made both selective and anisotropic, etches vertically but not laterally along the surface. In modern integrated circuit processing, the main use of wet chemical processing is in cleaning the wafers. Plasmas are ubiquitous in integrated circuit processing. The most popular type of plasma-based etching is known as reactive ion etching, Fig. 5.8. In a typical process, appropriate etch gases such as chlorofluorocarbons flow into the chamber at reduced pressure, 1 to 100 mTor, and a plasma is struck by applying an RF voltage across a cathode and an anode. The RF voltage accelerates the light electrons in the system to much higher kinetic energies, 10 electron volts, than the heavier ions. The high-energy electrons collide with neutral atoms and molecules to create ions and molecular fragments called radicals. The wafers are held on the radio frequency-powered cathode, while the grounded chamber walls act as the anode. From a study of plasma physics, we can show that although the bulk of the plasma is a highly conducting, equipotential region, less conducting sheath regions form next to the two electrodes. It can also be shown that the sheath voltage next to the cathode can be increased by making the powered cathode smaller in area than the grounded anode. A high DC voltage, 100 to 1000 V, develops across the sheath next to the RF powered cathode, such that positive ions gain kinetic energy by being accelerated in this region, and bombard the wafer normal to the surface. This bombardment at normal incidence contributes a physical component to the etch that makes it anisotropic. Physical etching, however, is rather unselective. Simultaneously, the highly reactive radicals in the system give rise to a chemical etch component that is very selective, but not anisotropic. The result is that Re achieves a good compromise between anisotropy and selectivity, and has become the mainstay of modern integrated circuit etch technology. Figure 5.8. Reactive ion etcher. Single or multiple wafers are placed on the radio frequency powered cathode to maximize the ion bombardment. Shown in the figure is a simple diode etcher in which we have just two electrodes. We can also use a third electrode to supply radio frequency power separately to the etch gases in a triode etcher. The most commonly used radio frequency is 13.56 MHz, which is a frequency dedicated to industrial use so that there is minimal interference with radio communications. Metallization. After the semiconductor devices are made by the processing methods described previously, they have to be connected to each other, and ultimately to the integrated circuit package, by metallization. Metal films are generally deposited by a physical vapor deposition technique such as evaporation, for example, gold on gallium arsenide, or sputtering, for example, aluminum on silicon. Sputtering of aluminum is achieved by immersing an aluminum target, typically alloyed with 1, silicon and 4, copper to improve the electrical and metallurgical properties of the aluminum, as described in section 9.3.1, in an AR plasma. Argon ions bombard the aluminum and physically dislodge aluminum atoms by momentum transfer, Fig. 5.9. Many of the aluminum atoms ejected from the target deposit on the silicon wafers held in close proximity to the target. The aluminum is then patterned using the metallization reticle and subsequently etched by Re. Finally, it is sintered at 450 degrees Celsius for 30 minutes to form a good electrical, Ohmic contact to the silicon. Recently, for silicon integrated circuits, there has been a shift from aluminum to lower resistivity copper metallization. Copper cannot be deposited by sputtering. Instead, it is electroplated on the chips. Copper metallization introduces special challenges because copper diffuses fast in silicon, and acts as a deep trap. Hence, prior to the electroplating of copper, a barrier metal such as titanium is first sputter deposited to block copper diffusion into silicon. The titanium also acts as a seed layer for copper electrodeposition. After the interconnection metallization is complete, a protective overcoat of silicon nitride is deposited using plasma-enhanced chemical vapor deposition. Then the individual integrated circuits can be separated by sawing or by scribing and breaking the wafer. The final steps of the process are mounting individual devices in appropriate packages and connecting leads to the aluminum contact regions. Figure 5.9 Aluminum sputtering by argon-positive ions. The argon-positive ions with energies of 1 to 3 kV physically dislodge aluminum atoms which end up depositing on the silicon wafers held in close proximity. The chamber pressures are kept low such that the mean free path of the ejected aluminum atoms is long compared to the target to wafer separation. Figure 5.10 Simplified description of steps in the fabrication of p-n junctions. For simplicity, only 4 diodes per wafer are shown, and the relative thicknesses of the oxide, P-er, and the Al layers are exaggerated. 1. Oxidize the silicon sample. 2. Apply a layer of positive photoresist. 3. Expose photoresist through mask. 4. Remove exposed photoresist. 5. Use reactive ion etching to remove silicon dioxide in windows. 6. Implant boron through windows in the photoresist and silicon dioxide layers. 7. Remove photoresist and sputter aluminum onto the surface. 8. Using photoresist and mask B, repeat steps 2 to 4, etch away aluminum except in p-type semiconductor contact areas. Very precise lead bonders are available for bonding gold or aluminum wire, about 1/1000th of an inch in diameter, to the device and then to the package leads. This phase of device fabrication is called back-end processing, and is discussed in more detail in Chapter 9. The main steps in making p-n junctions using some of these unit processes are illustrated in Fig 5.10. Similarly, we will discuss how the key semiconductor devices are made using these same unit processes in subsequent chapters. In this chapter we wish to develop both a useful mathematical description of the p-n junction and a strong qualitative understanding of its properties. There must be some compromise in these two goals, since a complete mathematical treatment would obscure the essentially simple physical features of junction operation, while a completely qualitative description would not be useful in making calculations. The approach, therefore, will be to describe the junction mathematically while neglecting small effects which add little to the basic solution. In section 5.6 we shall include several deviations from the simple theory. The mathematics of p-n junctions is greatly simplified for the case of the step junction, which has uniform p doping on one side of a sharp junction and uniform n doping on the other side. This model represents epitaxial junctions quite well. Diffused or implanted junctions, however, are actually graded. Donors, acceptors varies over a significant distance on either side of the junction. After the basic ideas of junction theory are explored for the step junction, we can make the appropriate corrections to extend the theory to the graded junction. In these discussions we shall assume one-dimensional current flow in samples of uniform cross-sectional area. In this section we investigate the properties of the step junction at equilibrium, i.e., with no external excitation and no net currents flowing in the device. We shall find that the difference in doping on each side of the junction causes a potential difference between the two types of material. This is a reasonable result, since we would expect some charge transfer because of diffusion between the p material, many holes, and the n material, many electrons. In addition, we shall find that there are 4 components of current which flow across the junction due to the drift and diffusion of electrons and holes. These four components combine to give zero net current for the equilibrium case. However, the application of bias to the junction increases some of these current components with respect to others, giving net current flow. If we understand the nature of these four current components, a sound view of p-n junction operation, with or without bias, will follow. The contact potential. Let us consider separate regions of p and n-type semiconductor material, brought together to form a junction, Fig. 511. This is not a practical way of forming a device, but this thought experiment does allow us to discover the requirements of equilibrium at a junction. Before they are joined, the N material has a large concentration of electrons and few holes, whereas the converse is true for the P material. Upon joining the two regions, Fig. 511, we expect diffusion of carriers to take place because of the large carrier concentration gradients at the junction. Thus holes diffuse from the P side into the N side, and electrons diffuse from N to P. The resulting diffusion current cannot build up indefinitely, however, because an opposing electric field is created at the junction, Fig. 511b. If the two regions were boxes of red air molecules and green molecules, perhaps due to appropriate types of pollution, eventually there would be a homogeneous mixture of the two after the boxes were joined. This cannot occur in the case of the charged particles in a p-n junction because of the development of space charge and the electric field. If we consider that electrons diffusing from N to P leave behind uncompensated 3 donor ions in the N material, and holes leaving the P region leave behind uncompensated acceptors, it is easy to visualize the development of a region of positive space charge near the N side of the junction and negative charge near the P side. Figure 511. Properties of an equilibrium p-n junction. A. Isolated, neutral regions of p-type and n-type material and energy bands for the isolated regions. B. Junction, showing space charge in the transition region W, the resulting electric field, and contact potential V0, and the separation of the energy bands. C. Directions of the four components of particle flow within the transition region, and the resulting current directions. The resulting electric field is directed from the positive charge toward the negative charge. Thus is in the direction opposite to that of diffusion current for each type of carrier. Recall, electron current is opposite to the direction of electron flow. Therefore, the field creates a drift component of current from N to P, opposing the diffusion current, Fig. 511c. Since we know that no net current can flow across the junction at equilibrium, the current due to the drift of carriers in the field must exactly cancel the diffusion current. Furthermore, since there can be no net buildup of electrons or holes on either side as a function of time, the drift and diffusion currents must cancel for each type of carrier. Therefore, the electric field builds up to the point where the net current is zero at equilibrium. The electric field appears in some region W about the junction, and there is an equilibrium potential difference V0 across W. In the electrostatic potential diagram of Fig. 511b, there is a gradient in potential in the direction opposite to. In accordance with the fundamental relation, we assume the electric field is zero in the neutral regions outside W. Thus there is a constant potential N in the neutral N material, a constant P in the neutral P material, and a potential difference between the two. The region W is called the transition region, 5, and the potential difference V0 is called the contact potential. The contact potential appearing across W is a built-in potential barrier, in that it is necessary to the maintenance of equilibrium at the junction. It does not imply any external potential. Indeed, the contact potential cannot be measured by placing a voltmeter across the devices, because new contact potentials are formed at each probe, just cancelling V0. By definition, V0 is an equilibrium quantity, and no net current can result from it. The contact potential separates the bands as in Fig. 511b. The valence and conduction energy bands are higher on the P side of the junction than on the NSIDE6 by the amount QV0. The separation of the bands at equilibrium is just that required to make the Fermi level constant throughout the device. We discussed the lack of spatial variation of the Fermi level at equilibrium in section 3.5. Thus, if we know the band diagram, including F, for each separate material, Fig 511a, we can find the band separation for the junction at equilibrium simply by drawing a diagram such as Fig 511b with the Fermi levels aligned. To obtain a quantitative relationship between V0 and the doping concentrations on each side of the junction, we must use the requirements for equilibrium in the drift and diffusion current equations. For example, the drift and diffusion components of the whole current just cancel at equilibrium. This equation can be rearranged to obtain where the x direction is arbitrarily taken from P to N. The electric field can be written in terms of the gradient in the potential, x, equal, d, x, dx, so that EQ 5,4b, becomes, with the use of the Einstein relation for op dp. This equation can be solved by integration over the appropriate limits. In this case we are interested in the potential on either side of the junction, P and N, and the whole concentration just at the edge of the transition region on either side, Pages and Pn. For a step junction it is reasonable to take the electron and hole concentration in the neutral regions outside the transition region as their equilibrium values. Since we have assumed a one-dimensional geometry, P and can be taken reasonably as functions of x only. Integration of EQ 5,5 gives the potential difference N, P is the contact potential V0, Fig 511b. Thus we can write V0 in terms of the equilibrium hole concentrations on either side of the junction. If we consider the step junction to be made up of material with acceptors CM3 on the P side and a concentration of donors on the N side, we can write EQ 5,7 as, by considering the majority carrier concentration to be the doping concentration on each side. Another useful form of EQ 5,7 is, by using the equilibrium condition PPNP equal N2I equal PNNN, we can extend EQ 5,9 to include the electron concentrations on either side of the junction. This relation will be very valuable in calculation of the current voltage characteristics of the junction. An abrupt silicon PN junction has million trillion acceptors per cubic centimeter on one side and example 1,000 trillion donors per cubic centimeter on the other. A. Calculate the Fermi level positions at 300 K in the P and N regions. B. Draw an equilibrium band diagram for the junction and determine the contact potential V0 from the diagram. C. Compare the results of part B with V0 as calculated from EQ 5,8. Equilibrium Fermi levels. We have observed that the Fermi level must be constant throughout the device at equilibrium. This observation can be easily related to the results of the previous section. Since we have assumed that Pn and Pages are given by their equilibrium values outside the transition region, we can write EQ 5,9 in terms of the basic definitions of these quantities using EQ 319. The Fermi level and valence band energies are written with subscripts to indicate the P side and the N side of the junction. From Fig 511b the energy bands on either side of the junction are separated by the contact potential V0 times the electronic charge Q, thus the energy difference EV is just QV0. Equation 512 results from the fact that the Fermi levels on either side of the junction are equal at equilibrium, EFN, EFP equals 0. When bias is applied to the junction, the potential barrier is raised or lowered from the value of the contact potential, and the Fermi levels on either side of the junction are shifted with respect to each other by an energy in electron volts numerically equal to the applied voltage in volts. Space charge at a junction. Within the transition region, electrons and holes are in transit from one side of the junction to the other. Some electrons diffuse from N to P, and some are swept by the electric field from P to N, and conversely for holes, there are, however, very few carriers within the transition region at any given time, since the electric field serves to sweep out carriers which have wandered into W. To a good approximation, we can consider the space charge within the transition region as due only to the uncompensated donor and acceptor ions. The charge density within W is plotted in Fig 512b. Neglecting carriers within the space charge region, the charge density on the N side is just Q times the concentration of donor ions, and the negative charge density on the P side is Q times the concentration of acceptors. The assumption of carrier depletion within W and neutrality outside W is known as the depletion approximation. Figure 512. Space charge and electric field distribution within the transition region of a p-n junction with donors and acceptors. A. The transition region, with X equals 0 defined at the metallurgical junction. B. Charge density within the transition region, neglecting the free carriers. C. The electric field distribution, where the reference direction for is arbitrarily taken as the plus X at direction. Since the dipole about the junction must have an equal number of charges on either side, Q plus equal Q, the transition region may extend into the P and N regions unequally, depending on the relative doping of the two sides. For example, if the P side is more lightly doped than the N side, acceptors and donors, the space charge region must extend farther into the P material than into the N, to uncover an equivalent amount of charge. For a sample of cross-sectional area A, the total uncompensated charge on either side of the junction is, where xp0 is the penetration of the space charge region into the P material, and xn0 is the penetration into N. The total width of the transition region, W, is the sum of xp0 and xn0. To calculate the electric field distribution within the transition region, we begin with Poisson's equation, which relates the gradient of the electric field to the local space charge at any point x. This equation is greatly simplified within the transition region if we neglect the contribution of the carriers, Pn, to the space charge. With this approximation we have two regions of constant space charge. Assuming complete ionization of the impurities donors and acceptors, we can see from these two equations that a plot of x versus x within the transition region has two slopes, positive, increasing with x, on the N side, and negative, becoming more negative as x increases, on the P side. There is some maximum value of the field 0 at x equals 0, the metallurgical junction between the P and N materials, and x is everywhere negative within the transition region, Fig 512c. These conclusions come from Gauss's law, but we could predict the qualitative features of Fig 512 without equations. We expect the electric field, x, to be negative throughout W, since we know that the field actually points in the x at direction, from N to P, i.e., from the positive charges of the transition region dipole toward the negative charges. The electric field is assumed to go to 0 at the edges of the transition region, since we are neglecting any small field in the neutral N or P regions. Finally, there must be a maximum 0 at the junction, since this point is between the charges Q plus and Q, on either side of the transition region. All the electric flux lines pass through the x equals 0 plane, so this is the obvious point of maximum electric field. The value of 0 can be found by integrating either part of EQ. 515, with appropriate limits, see Fig 512c in choosing the limits of integration. Therefore, the maximum value of the electric field is. It is simple to relate the electric field to the contact potential V0, since the field at any x is the negative of the potential gradient at that point. Thus the negative of the contact potential is simply the area under the x versus x triangle. This relates the contact potential to the width of the depletion region. Since the balance of charge requirement is xn0 donors equal xp0 acceptors, and W is simply xp0 plus xn0, we can write xn0 equal WNA, acceptors plus donors, in EQ. 519. By solving for W, we have an expression for the width of the transition region in terms of the contact potential, the doping concentrations, and known constants Q and P. There are several useful variations of EQ. 521, for example, V0 can be written in terms of the doping concentrations with the aid of EQ. 58. We can also calculate the penetration of the transition region into the N and P materials. As expected, EQs. 523, predict that the transition region extends farther into the side with the lighter doping. For example, if acceptors, donors, XP0 is large compared with XN0. This agrees with our qualitative argument that a deep penetration is necessary in lightly doped material to uncover the same amount of space charge as for a short penetration into heavily doped material. Another important result of EQ 521 is that the transition width W varies as the square root of the potential across the region. In the derivation to this point, we have considered only the equilibrium contact potential V0. In section 5.3 we shall see that an applied voltage can increase or decrease the potential across the transition region by aiding or opposing the equilibrium electric field. Therefore, EQ 521 predicts that an applied voltage will increase or decrease the width of the transition region as well. The junction described in example 5.1 has a circular cross-section with a diameter of 10 mm. Calculate XN0, XP0, Q+, and 0 for this junction at equilibrium, 300 K. Sketch X, and charge density to scale, as in Fig 512. One useful feature of a p-n junction is that current flows quite freely in the p to n direction when the p region has a positive external voltage bias relative to n, forward bias and forward current, whereas virtually no current flows. When P is made negative relative to N, reverse bias and reverse current. This asymmetry of the current flow makes the p-n junction diode very useful as a rectifier. While rectification is an important application, it is only the beginning of a host of uses for the biased junction. Biased p-n junctions can be used as voltage variable capacitors, photocells, light emitters, and many more devices which are basic to modern electronics. Two or more junctions can be used to form transistors and controlled switches. In this section we begin with a qualitative description of current flow in a biased junction. With the background of the previous section, the basic features of current flow are relatively simple to understand, and these qualitative concepts form the basis for the analytical description of forward and reverse currents in a junction. Qualitative description of current flow at a junction. We assume that an applied voltage bias V appears across the transition region of the junction rather than in the neutral N and P regions. Of course, there will be some voltage drop in the neutral material, if a current flows through it. But in most p-n junction devices, the length of each region is small compared with its area, and the doping is usually moderate to heavy, thus the resistance is small in each neutral region, and only a small voltage drop can be maintained outside the space charge, transition, region. For almost all calculations it is valid to assume that an applied voltage appears entirely across the transition region. We shall take V to be positive when the external bias is positive on the P side relative to the N side. Since an applied voltage changes the electrostatic potential barrier and thus the electric field within the transition region, we would expect changes in the various components of current at the junction, Fig 513. In addition, the separation of the energy bands is affected by the applied bias, along with the width of the depletion region. Let us begin by examining qualitatively the effects of bias on the important features of the junction. The electrostatic potential barrier at the junction is lowered by a forward bias Vf from the equilibrium contact potential V0 to the smaller value V0, Vf. This lowering of the potential barrier occurs because a forward bias, P positive with respect to N, raises the electrostatic potential on the P side relative to the N side. For a reverse bias, V equal, Vr, the opposite occurs, the electrostatic potential of the P side is depressed relative to the N side, and the potential barrier at the junction becomes larger, V0 plus Vr. The electric field within the transition region can be deduced from the potential barrier. We notice that the field decreases with forward bias, since the applied electric field opposes the built-in field. With reverse bias, the field at the junction is increased by the applied field, which is in the same direction as the equilibrium field. The change in electric field at the junction calls for a change in the transition region width W, since it is still necessary that a proper number of positive and negative charges, in the form of uncompensated donor and acceptor ions, be exposed for a given value of the field. Thus we would expect the width W to decrease under forward bias, smaller, fewer uncompensated charges, and to increase under reverse bias. Equations 521 and 523 can be used to calculate W, xp0, and xn0 if V0 is replaced by the new barrier height 8V0, V. The separation of the energy bands is a direct function of the electrostatic potential barrier at the junction. The height of the electron energy barrier is simply the electronic charge Q times the height of the electrostatic potential barrier. Thus the bands are separated less Q, V0, Vf, under forward bias than at equilibrium, and more Q, V0 plus Vr, under reverse bias. We assume the Fermi level deep inside each neutral region is essentially the equilibrium value. We shall return to this assumption later. Therefore, the shifting of the energy bands under bias implies a separation of the Fermi levels on either side of the junction, as mentioned in section 5.2.2. Under forward bias, the Fermi level on the N side EFN is above EFP by the energy QVF. For reverse bias, EFP is QVR joules higher than EFN. In energy units of electron volts, the Fermi levels in the two neutral regions are separated by an energy, electron volts, numerically equal to the applied voltage, V. The diffusion current is composed of majority carrier electrons on the N side surmounting the potential energy barrier to diffuse to the P side, and holes surmounting their barrier from P to N9. There is a distribution of energies for electrons in the N-side conduction band, Fig 316, and some electrons in the high-energy tail of the distribution have enough energy to diffuse from N to P at equilibrium in spite of the barrier. With forward bias, however, the barrier is lowered, to V0, Vf, and many more electrons in the N-side conduction band have sufficient energy to diffuse from N to P over the smaller barrier. Therefore, the electron diffusion current can be quite large with forward bias. Similarly, more holes can diffuse from P to N under forward bias because of the lowered barrier. For reverse bias, the barrier becomes so large, V0 plus Vr, that virtually no electrons in the N-side conduction band or holes in the P-side valence band have enough energy to surmount it. Therefore, the diffusion current is usually negligible for reverse bias. The drift current is relatively insensitive to the height of the potential barrier. This sounds strange at first, since we normally think in terms of material with ample carriers, and therefore we expect drift current to be simply proportional to the applied field. The reason for this apparent anomaly is the fact that the drift current is limited not by how fast carriers are swept down the barrier, but rather how often. For example, minority carrier electrons on the P side which wander into the transition region will be swept down the barrier by the field, giving rise to the electron component of drift current. However, this current is small not because of the size of the barrier, but because there are very few minority electrons in the P side to participate. Every electron on the P side which diffuses to the transition region will be swept down the potential energy hill, whether the hill is large or small. The electron drift current does not depend on how fast an individual electron is swept from P to N, but rather on how many electrons are swept down the barrier per second. Similar comments apply regarding the drift of minority holes from the N side to the P side of the junction. To a good approximation, therefore, the electron and hole drift currents at the junction are independent of the applied voltage. The supply of minority carriers on each side of the junction required to participate in the drift component of current is generated by thermal excitation of electron-hole pairs, EHPs. For example, an electron-hole pair created near the junction on the p side provides a minority electron in the p material. If the electron-hole pair is generated within a diffusion length Ln of the transition region, this electron can diffuse to the junction and be swept down the barrier to the n side. The resulting current due to drift of generated carriers across the junction is commonly called the generation current, since its magnitude depends entirely on the rate of generation of electron-hole pairs. As we shall discuss later, this generation current can be increased greatly by optical excitation of electron-hole pairs near the junction, the p-n junction photodiode. The total current crossing the junction is composed of the sum of the diffusion and drift components. As Fig 5.13 indicates, the electron and hole diffusion currents are both directed from p to n, although the particle flow directions are opposite to each other, and the drift currents are from n to p. The net current crossing the junction is zero at equilibrium. Since the drift and diffusion components cancel for each type of carrier, the equilibrium electron and hole components need not be equal, as in Fig 5.13, as long as the net hole current and the net electron current are each zero. Under reverse bias, both diffusion components are negligible because of the large barrier at the junction, and the only current is the relatively small, and essentially voltage independent, generation current from n to p. This generation current is shown in Fig 5.14, in a sketch of a typical IV plot for a p-n junction. In this figure, the positive direction for the current I is taken from P to N, and the applied voltage V is positive when the positive battery terminal is connected to P and the negative terminal to N. The only current flowing in this p-n junction diode for negative V is the small current I, general, due to carriers generated in the transition region or minority carriers which diffuse to the junction and are collected. The current at V equals 0, equilibrium, is zero since the generation and diffusion currents cancel. The total current I is the sum of the generation and diffusion components. However, these components are oppositely directed, with I, div, being positive and I, general, being negative for the chosen reference direction. To avoid confusion of signs, we use here the magnitude of the drift current I, general, and include its negative sign in EQ. 5.24. Thus, when we write the term I, general, there is no doubt that the generation current is in the negative current direction. This approach emphasizes the fact that the two components of current add with opposite signs to give the total current. As we shall see in the next section, an applied forward bias V equal Vf increases the probability that a carrier can diffuse across the junction, by the factor exp, qVf caret. Thus the diffusion current under forward bias is given by its equilibrium value multiplied by exp, qV caret. Similarly, for reverse bias the diffusion current is the equilibrium value reduced by the same factor, with V equal, Vr. Since the equilibrium diffusion current is equal in magnitude to current, generated, the diffusion current with applied bias is simply current, generated, exp, qV caret. The total current I is then the diffusion current minus the absolute value of the generation current, which we will now refer to as I0. In EQ 5.25, the applied voltage V can be positive or negative, V equal Vf or V equal, Vr. When V is positive and greater than a few caret Q equals 0.0259 V at room temperature, the exponential term is much greater than unity. The current thus increases exponentially with forward bias. When V is negative, reverse bias, the exponential term approaches zero and the current is I0, which is in the n to p, negative, direction. This negative generation current is also called the reverse saturation current. The striking feature of Fig 5.14 is the nonlinearity of the IV characteristic. Current flows relatively freely in the forward direction of the diode, but almost no current flows in the reverse direction. Carrier injection. From the discussion in the previous section, we expect the minority carrier concentration on each side of a p-n junction to vary with the applied bias because of variations in the diffusion of carriers across the junction. The equilibrium ratio of hole concentrations on each side becomes with bias, Fig 5.13. This equation uses the altered barrier V0, V to relate the steady-state hole concentrations on the two sides of the transition region with either forward or reverse bias, V positive or negative. For low-level injection we can neglect changes in the majority carrier concentrations. Although the absolute increase of the majority carrier concentration is equal to the increase of the minority carrier concentration in order to maintain space charge neutrality, the relative change in majority carrier concentration can be assumed to vary only slightly with bias compared with equilibrium values. With this simplification we can write the ratio of EQ 526 to 527 as, with forward bias, EQ 528 suggests a greatly increased minority carrier hole concentration at the edge of the transition region on the n side p, x n0, than was the case at equilibrium. Conversely, the hole concentration p, x n0, under reverse bias, V negative, is reduced below the equilibrium value Pn. The exponential increase of the hole concentration at xn0 with forward bias is an example of minority carrier injection. As Fig 5.15 suggests, a forward bias V results in a steady-state injection of excess holes into the N region and electrons into the P region. We can easily calculate the excess hole concentration Pn at the edge of the transition region xn0 by subtracting the equilibrium hole concentration from EQ 528. And similarly for excess electrons on the p side. From our study of diffusion of excess carriers in section 4.4.4, we expect that injection leading to a steady concentration of Pn excess holes at xn0 will produce a distribution of excess holes in the N material. As the holes diffuse deeper into the N region, they recombine with electrons in the N material, and the resulting excess hole distribution is obtained as a solution of the diffusion equation, EQ 434b. If the N region is long compared with the hole diffusion length Lp, the solution is exponential, as in EQ 436. Similarly, the injected electrons in the P material diffuse and recombine, giving an exponential distribution of excess electrons. For convenience, let us define two new coordinates, Fig 5.15, distances measured in the x direction in the N material from xn0 will be designated xn, distances in the P material measured in the x at direction with xp0 as the origin will be called x. P. Figure 5.15. Forward biased junction, A, minority carrier distributions on the two sides of the transition region and definitions of distances xn and xp measured from the transition region edges, B, variation of the quasi-Fermi levels with position. This convention will simplify the mathematics considerably. We can write the diffusion equation as in EQ 434, for each side of the junction and solve for the distributions of excess carriers, dn and dp, assuming long P and N regions. The hole diffusion current at any point xn in the N material can be calculated from EQ 440, where A is the cross-sectional area of the junction. Thus the hole diffusion current at each position xn is proportional to the excess hole concentration at that point 11. The total hole current injected into the N material at the junction can be obtained simply by evaluating EQ 532 at xn0. By a similar analysis, the injection of electrons into the P material leads to an electron current at the junction of the minus sign in EQ 534, means that the electron current is opposite to the xp direction, that is, the true direction of in is in the plus x at direction, adding to Ip in the total current, Fig 5.16. If we neglect recombination in the transition region, which is known as the Shockley ideal diode approximation, we can consider that each injected electron reaching xp0 must pass through xn0. Thus the total diode current I at Xn0 can be calculated as the sum of IP, Xn equals 0, and, in, Xp equals 0. If we take the plus X at direction as the reference direction for the total current I, we must use a minus sign within, Xp, to account for the fact that Xp is defined in the X at direction. Equation 536 is the diode equation, having the same form as the qualitative relation EQ. 525. Nothing in the derivation excludes the possibility that the bias voltage V can be negative, thus the diode equation describes the total current through the diode for either forward or reverse bias. We can calculate the current for reverse bias by letting V equal VR. If VR is larger than a few carat Q, the total current is just the reverse saturation current. Figure 516. Two methods for calculating junction current from the excess minority carrier distributions: A. Diffusion currents at the edges of the transition region, B. Charge in the distributions divided by the minority carrier lifetimes, C. The diode equation. 1 implication of EQ. 536 is that the total current at the junction is dominated by injection of carriers from the more heavily doped side into the side with lesser doping. For example, if the P material is very heavily doped and the N region is lightly doped, the minority carrier concentration on the P side, NP, is negligible compared with the minority carrier concentration on the N side, PN. Thus the diode equation can be approximated by injection of holes only, as in EQ. 533. This means that the charge stored in the minority carrier distributions is due mostly to holes on the N side. For example, to double the hole current in this P+, N junction one should not double the P+ doping, but rather reduce the N-type doping by a factor of 2. This structure is called a P+, N junction, where the plus superscript simply means heavy doping. Another characteristic of the P+, N or N+, P structure is that the transition region extends primarily into the lightly doped region, as we found in the discussion of EQ. 523. Having one side heavily doped is a useful arrangement for many practical devices, as we shall see in our discussions of switching diodes and transistors. This type of junction is common in devices which are fabricated by counterdoping. For example, an N-type silicon sample with 100 trillion donors per cubic centimeter can be used as the substrate for an implanted or diffused junction. If the doping of the P region is greater than 10 million trillion per cubic centimeter, typical of diffused junctions, the structure is definitely P+, N, with NP more than 5 orders of magnitude smaller than Pn. Since this configuration is common in device technology, we shall return to it in much of the following discussion. Figure 515b shows the quasi-Fermi levels as a function of position for a P-N junction in forward bias. The equilibrium F is split into the quasi-Fermi levels Fn and Fp, which are separated within W by an energy QV caused by the applied bias, V. This energy represents the deviation from equilibrium, see section 4.3.3. In forward bias in the depletion region we thus get, on either side of the junction, it is the minority carrier quasi-Fermi level that varies the most. The majority carrier concentration is not affected much, so the majority carrier quasi-Fermi level is close to the original F. Although there is some variation in F and Fp within W, it doesn't show up on the scale used in Fig 515. Outside of the depletion regions, the quasi-Fermi levels for the minority carriers vary linearly and eventually merge with the Fermi levels. In contrast, the minority carrier concentrations decay exponentially with distance. In fact, it takes many diffusion lengths for the quasi-Fermi level to cross EI, where the minority carrier concentration is equal to the intrinsic carrier concentration, let alone approach F, where for example dP, Xn, Pn. Another simple and instructive way of calculating the total current is to consider the injected current as supplying the carriers for the excess distributions, Fig 516b. For example, IP, xn equals 0, must supply enough holes per second to maintain the steady-state exponential distribution P, xn, as the holes recombine. The total positive charge stored in the excess carrier distribution at any instant of time is the average lifetime of a hole in the n-type material is Vp. Thus, on the average, this entire charge distribution recombines and must be replenished every Vp seconds. The injected hole current at xn equals 0 needed to maintain the distribution is simply the total charge divided by the average time of replacement. This is the same result as EQ 533, which was calculated from the diffusion currents. Similarly, we can calculate the negative charge stored in the distribution dN, xp, and divide by Vn to obtain the injected electron current in the P material. This method, called the charge control approximation, illustrates the important fact that the minority carriers injected into either side of a p-n junction diffuse into the neutral material and recombine with the majority carriers. The minority carrier current, for example, IP, xn, decreases exponentially with distance into the neutral region. Thus, several diffusion lengths away from the junction, most of the total current is carried by the majority carriers. We shall discuss this point in more detail later in this section. In summary, we can calculate the current at a p-n junction in two ways, Fig 516, a, from the slopes of the excess minority carrier distributions at the two edges of the transition regions, and b, from the steady-state charge stored in each distribution. We add the hole current injected into the n material IP, xn equals 0, to the electron current injected into the p material IP, xp equals 0. After including a minus sign within xp, to conform with the conventional definition of positive current in the plus x at direction, we are able to add these two currents because of the assumption that no recombination takes place within the transition region. Thus we effectively have the total electron and hole current at one point in the device, xn0. Since the total current must be constant throughout the device, despite variations in the current components, I as described by EQ 536, is the total current at every position x in the diode. The drift of minority carriers can be neglected in the neutral regions outside W, because the minority carrier concentration is small compared with that of the majority carriers. If the minority carriers contribute to the total current at all, their contribution must be through diffusion, dependent on the gradient of the carrier concentration. Even a very small concentration of minority carriers can have an appreciable effect on the current if the spatial variation is large. Calculation of the majority carrier currents in the two neutral regions is simple, once we have found the minority carrier current. Since the total current I must be constant throughout the device, the majority carrier component of current at any point is just the difference between I and the minority component, Fig 517. For example, since IP, xn, is proportional to the excess hole concentration at each position in the n material EQ 532, it decreases exponentially in xn with the decreasing dp, xn. Thus the electron component of current must increase appropriately with xn to maintain the total current I. Far from the junction, the current in the n material is carried almost entirely by electrons. The physical explanation of this is that electrons must flow in from the n material, and ultimately from the negative terminal of the battery, to resupply electrons lost by recombination in the excess hole distribution near the junction. The electron current in xn includes sufficient electron flow to supply not only recombination near xn0, but also injection of electrons into the p region. Of course, the flow of electrons in the n material toward the junction constitutes a current in the plus x at direction, contributing to the total current I. One question that still remains to be answered is whether the majority carrier current is due to drift or diffusion or both, at different points in the diode. Near the junction, just outside of the depletion regions, the majority carrier concentration changes by exactly the same amount as minority carriers in order to maintain space charge neutrality. the majority carrier concentration can change rather fast, in a very short time scale known as the dielectric relaxation time, Vd, equal Rp, where R is the resistivity and P is the dielectric constant. The relaxation time Td is the analog of the Rc time constant in a circuit. Very far away from the junction, more than 3 to 5 diffusion lengths, the minority carrier concentration decays to a low, constant background value. Hence, the majority carrier concentration also becomes independent of position. Here, clearly the only possible current component is majority carrier drift current. When approaching the junction there is a spatially varying majority, and minority, carrier concentration and the majority carrier current changes from pure drift to drift and diffusion, although drift always dominates for majority carriers except in cases of very high levels of injection. Throughout the diode, the total current due to majority and minority carriers at any cross-section is kept constant. We thus note that the electric field in the neutral regions cannot be zero as we previously assumed, otherwise, there would be no drift currents. Thus our assumption that all of the applied voltage appears across the transition region is not completely accurate. On the other hand, the majority carrier concentrations are usually large in the neutral regions, so that only a small field is needed to drive the drift currents. Thus the assumption that junction voltage equals applied voltage is acceptable for most calculations. Find an expression for the electron current in the N-type material of a forward-biased p-N junction. The total current is. The whole current on the N side is. Thus the electron current in the N material is. This expression includes the supplying of electrons for recombination with the injected holes, and the injection of electrons across the junction into the P side. Reverse bias. In our discussion of carrier injection and minority carrier distributions, we have primarily assumed forward bias. The distributions for reverse bias can be obtained from the same equations, Fig 518, if a negative value of V is introduced. For example, if V equal, VR, P negatively biased with respect to N, we can approximate EQ 529, as and similarly NP. Thus for a reverse bias of more than a few tenths of a volt, the minority carrier concentration at each edge of the transition region becomes essentially zero as the excess concentration approaches the negative of the equilibrium concentration. The excess minority carrier concentrations in the neutral regions are still given by EQ 531, so that depletion of carriers below the equilibrium values extends approximately a diffusion length beyond each side of the transition region. This reverse bias depletion of minority carriers can be thought of as minority carrier extraction, analogous to the injection of forward bias. Physically, extraction occurs because minority carriers at the edges of the depletion region are swept down the barrier at the junction to the other side and are not replaced by an opposing diffusion of carriers. For example, when holes at X and 0 are swept across the junction to the P side by the field, a gradient in the hole distribution in the N material exists, and holes in the N region diffuse toward the junction. The steady-state hole distribution in the N region has the inverted exponential shape of Fig 518a. It is important to remember that although the reverse saturation current occurs at the junction by drift of carriers down the barrier, this current is fed from each side by diffusion toward the junction of minority carriers in the neutral regions. The rate of carrier drift across the junction, reverse saturation current, depends on the rate at which holes arrive at X and 0, and electrons at XP0, by diffusion from the neutral material. These minority carriers are supplied by thermal generation, and we can show that the expression for the reverse saturation current, EQ 538, represents the rate at which carriers are generated thermally within a diffusion length of each side of the transition region. In reverse bias, the quasi-Fermi levels split in the opposite sense than in forward bias, Fig 518b. The Fn moves farther away from EC, close to EV, and Fp moves farther away from EV, reflecting the fact that in reverse bias we have fewer carriers than in equilibrium, unlike the forward bias case where we have an excess of carriers. In reverse bias, in the depletion region, we have. It is interesting to note that the quasi-Fermi levels in reverse bias can go inside the bands. For example, Fp goes inside the conduction band on the N side of the depletion region. However, we must remember that Fp is a measure of the whole concentration, and should be correlated with the valence band edge, EV, and not with EC. Hence, the band diagram simply reflects the fact that we have very few holes in this region, even fewer than the already small equilibrium minority carrier hole concentration, Fig 518a. Similar observations can be made about the electrons. An abrupt silicon p-n junction, A equal 10 to 4 square centimeters, has the following properties at 300 K. We have found that a p-n junction biased in the reverse direction exhibits a small, essentially voltage-independent saturation current. This is true until a critical reverse bias is reached, for which reverse breakdown occurs. Fig 519. At this critical voltage, VBR, the reverse current through the diode increases sharply, and relatively large currents can flow with little further increase in voltage. The existence of a critical breakdown voltage introduces almost a right angle appearance to the reverse characteristic of most diodes. There is nothing inherently destructive about reverse breakdown. If the current is limited to a reasonable value by the external circuit, the p-n junction can be operated in reverse breakdown as safely as in the forward bias condition. For example, the maximum reverse current which can flow in the device of Fig 519 is E, VBR, R. The series resistance R can be chosen to limit the current to a safe level for the particular diode used. If the current is not limited externally, the junction can be damaged by excessive reverse current, which overheats the device as the maximum power rating is exceeded. It is important to remember, however, that such destruction of the device is not necessarily due to mechanisms unique to reverse breakdown. Similar results occur if the device passes excessive current in the forward direction 12, as we shall see in section 5.4.4. Useful devices called breakdown diodes are designed to operate in the reverse breakdown regime of their characteristics. Reverse breakdown can occur by two mechanisms, each of which requires a critical electric field in the junction transition region. The first mechanism, called the Zener effect, is operative at low voltages, up to a few volts reverse bias. If the breakdown occurs at higher voltages, from a few volts to thousands of volts, the mechanism is avalanche breakdown. We shall discuss these two mechanisms in this section. Zener breakdown. When a heavily doped junction is reverse biased, the energy bands become crossed at relatively low voltages, i.e., the N-side conduction band appears opposite the P-side valence band. As Fig 520 indicates, the crossing of the bands aligns the large number of empty states in the N-side conduction. Figure 520. The Zener effect, A, heavily doped junction at equilibrium, B, reverse bias with electron tunneling from P to N, C, IV characteristic. Band opposite the many filled states of the P-side valence band. If the barrier separating these two bands is narrow, tunneling of electrons can occur, as discussed in section 2.4.4. Tunneling of electrons from the P-side valence band to the N-side conduction band constitutes a reverse current from N to P. This is the Zener effect. The basic requirements for tunneling current are a large number of electrons separated from a large number of empty states by a narrow barrier of finite height. Since the tunneling probability depends upon the width of the barrier, D in Fig 520, it is important that the metallurgical junction be sharp and the doping high, so that the transition region W extends only a very short distance from each side of the junction. If the junction is not abrupt, or if either side of the junction is lightly doped, the transition region W will be too wide for tunneling. As the bands are crossed, at a few tenths of a volt for a heavily doped junction, the tunneling distance D may be too large for appreciable tunneling. However, D becomes smaller as the reverse bias is increased, because the higher electric fields result in steeper slopes for the band edges. This assumes that the transition region width W does not increase appreciably with reverse bias. For low voltages and heavy doping on each side of the junction, this is a good assumption. However, if Zener breakdown does not occur with reverse bias of a few volts, avalanche breakdown will become dominant. In the simple covalent bonding model, Fig 3.1, the Zener effect can be thought of as field ionization of the host atoms at the junction. That is, the reverse bias of a heavily doped junction causes a large electric field within W. At a critical field strength, electrons participating in covalent bonds may be torn from the bonds by the field and accelerated to the N side of the junction. The electric field required for this type of ionization is on the order of 106 V/centimeter. Avalanche breakdown. For lightly doped junctions, electron tunneling is negligible, and instead, the breakdown mechanism involves the impact ionization of host atoms by energetic carriers. Normal lattice scattering events can result in the creation of electron-hole pairs if the carrier being scattered has sufficient energy. For example, if the electric field in the transition region is large, an electron entering from the p side may be accelerated to high enough kinetic energy to cause an ionizing collision with the lattice, Fig 521a. A single such interaction results in carrier multiplication. The original electron and the generated electron are both swept to the N side of the junction, and the generated hole is swept to the p side, Fig 521b. The degree of multiplication can become very high if carriers generated within the transition region also have ionizing collisions with the lattice. For example, an incoming electron may have a collision with the lattice and create an electron-hole pairs. Each of these carriers has a chance of creating a new electron-hole pairs, and each of those can also create an electron-hole pairs, and so forth, Fig 521c. Figure 521 electron-hole pairs created by impact ionization, a band diagram of a p-n junction in reverse bias showing a primary electron gaining kinetic energy in the field of the depletion region, and creating a secondary electron-hole pair by impact ionization, the primary electron losing most of its kinetic energy in the process, b. A single ionizing collision by an incoming electron in the depletion region of the junction, c. Primary, secondary, and tertiary collisions. This is an avalanche process, since each incoming carrier can initiate the creation of a large number of new carriers. We can make an approximate analysis of avalanche multiplication by assuming that a carrier of either type has a probability p of having an ionizing collision with the lattice while being accelerated a distance w through the transition region. Thus for nin electrons entering from the p side, there will be nin ionizing collisions and an electron-hole pairs, secondary carriers, for each collision. After the nin collisions by the primary electrons, we have the primary plus the secondary electrons, nin, 1 plus p. After a collision, each electron-hole pairs moves effectively a distance of w within the transition region. For example, if an electron-hole pair is created at the center of the region, the electron drifts a distance w2 to n and the hole w2 to p. Thus the probability that an ionizing collision will occur due to the motion of the secondary carriers is still p in this simplified model. For nin-p secondary pairs there will be, nin-p, p ionizing collisions and nin-p2 tertiary pairs. Summing up the total number of electrons out of the region at n after many collisions, we have assuming no recombination. In a more comprehensive theory we would include recombination as well as different probabilities for ionizing collisions by electrons and holes. In our simple theory, the electron multiplication Mn is as can be verified by direct division. As the probability of ionization P approaches unity, the carrier multiplication, and therefore the reverse current through the junction, increases without limit. Actually, the limit on the current will be dictated by the external circuit. The relation between multiplication and P was easy to write in EQ 544a, however, the relation of P to parameters of the junction is much more complicated. Physically, we expect the ionization probability to increase with increasing electric field, and therefore to depend on the reverse bias. Measurements of carrier multiplication M in junctions near breakdown lead to an empirical relation where the exponent n varies from about 3 to 6, depending on the type of material used for the junction. In general, the critical reverse voltage for breakdown increases with the band gap of the material, since more energy is required for an ionizing collision. Also, the peak electric field within W increases with increased doping on the more lightly doped side of the junction. Therefore, VBR decreases as the doping increases, as Fig 522 indicates. Figure 522 variation of avalanche breakdown voltage in abrupt P+, N junctions, as a function of donor concentration on the N side, for several semiconductors. After S. M. Shi and G. Gibbons, Applied Physics Letters, Vol. 8. Rectifiers. The most obvious property of a p-n junction is its unilateral nature, that is, to a good approximation it conducts current in only one direction. We can think of an ideal diode as a short circuit when forward biased and as an open circuit when reverse biased, Fig 523a. The p-n junction diode does not quite fit this description, but the IV characteristics of many junctions can be approximated by the ideal diode in series with other circuit elements to form an equivalent circuit. For example, most forward biased diodes exhibit an offset voltage E0, see Fig 533, which can be approximated in a circuit model by a battery in series with the ideal diode, Fig 523b. Figure 523. Piecewise linear approximations of junction diode characteristics, A. The ideal diode, B. Ideal diode with an offset voltage, C. Ideal diode with an offset voltage and a resistance to account for slope in the forward characteristic. The series battery in the model keeps the ideal diode turned off for applied voltages less than E0. From section 5.6.1 we expect E0 to be approximately the contact potential of the junction. In some cases the approximation to the actual diode characteristic is improved by adding a series resistor R to the circuit equivalent, Fig 523c. The equivalent circuit approximations illustrated in Fig 523 are called piecewise linear equivalents, since the approximate characteristics are linear over specific ranges of voltage and current. An ideal diode can be placed in series with an AC voltage source to provide rectification of the signal. Since current can flow only in the forward direction through the diode, only the positive half cycles of the input sine wave are passed. The output voltage is a half rectified sine wave. Whereas the input sinusoid has zero average value, the rectified signal has a positive average value and therefore contains a DC component. By appropriate filtering, this DC level can be extracted from the rectified signal. The unilateral nature of diodes is useful for many other circuit applications that require wave shaping. This involves alteration of AC signals by passing only certain portions of the signal while blocking other portions. Junction diodes designed for use as rectifiers should have current voltage characteristics as close as possible to that of the ideal diode. The reverse current should be negligible, and the forward current should exhibit little voltage dependence, negligible forward resistance R. The reverse breakdown voltage should be large, and the offset voltage E0 in the forward direction should be small. Unfortunately, not all of these requirements can be met by a single device. Compromises must be made in the design of the junction to provide the best diode for the intended application. From the theory derived in section 5.3 we can easily list the various requirements for good rectifier junctions. Band gap is obviously an important consideration in choosing a material for rectifier diodes. Since Ni is small for large band gap materials, the reverse saturation current, which depends on thermally generated carriers, decreases with increasing e.g. A rectifier made with a wide band gap material can be operated at higher temperatures, because thermal excitation of electron-hole pairs is reduced by the increased band gap. Such temperature effects are critically important in rectifiers, which must carry large currents in the forward direction and are thereby subjected to appreciable heating. On the other hand, the contact potential and offset voltage E0 generally increase with e.g. This drawback is usually outweighed by the advantages of low Ni. For example, Si is generally preferred over germanium for power rectifiers because of its wider band gap, lower leakage current, and higher breakdown voltage, as well as its more convenient fabrication properties. The doping concentration on each side of the junction influences the avalanche breakdown voltage, the contact potential, and the series resistance of the diode. If the junction has one highly doped side and one lightly doped side, such as AP+, N junction, the lightly doped region determines many of the properties of the junction. From Fig 522 we see that a high resistivity region should be used for at least one side of the junction to increase the breakdown voltage VBR. However, this approach tends to increase the forward resistance R of Fig 523C, and therefore contributes to the problems of thermal effects due to I2R heating. To reduce the resistance of the lightly doped region, it is necessary to make its area large and reduce its length. Therefore, the physical geometry of the diode is another important design variable. Limitations on the practical area for a diode include problems of obtaining uniform starting material and junction processing over large areas. Localized flaws in junction uniformity can cause premature reverse breakdown in a small region of the device. Similarly, the lightly doped region of the junction cannot be made arbitrarily short. One of the primary problems with a short, lightly doped region is an effect called punch-through. Since the transition region width W increases with reverse bias and extends primarily into the lightly doped region, it is possible for W to increase until it fills the entire length of this region, Prop 5.30. The result of punch-through is a breakdown below the value of VBR expected from Fig 522. In devices designed for use at high reverse bias, care must be taken to avoid premature breakdown across the edge of the sample. This effect can be reduced by beveling the edge or by diffusing a guard ring to isolate the junction from the edge of the sample, Fig 524. The electric field is lower at the beveled edge of the sample in Fig 524b than it is in the main body of the device. Similarly, the junction at the lightly doped P-guard ring of Fig 524c breaks down at higher voltage than the P+N junction. Since the depletion region is wider in the P ring than in the P+ region, the average electric field is smaller at the ring for a given diode reverse voltage. In fabricating a P+, N or AP at N+ junction, it is common to terminate the lightly doped region with a heavily doped layer of the same type, Fig 525a, to ease the problem of making ohmic contact to the device. The result is a P+ at N+ structure with the P at N+ layer serving as the active junction, or a P+ at N+ device with an active P at N+ junction. The lightly doped center region determines the avalanche breakdown voltage. If this region is short compared with the minority carrier diffusion length, the excess carrier injection for large forward currents can increase the conductivity of the region significantly. This type of conductivity modulation, which reduces the forward resistance R, can be very useful for high current devices. On the other hand, a short, lightly doped center region can also lead to punch-through under reverse bias, as in Fig 525c. Figure 524 beveled edge and guard ring to prevent edge breakdown under reverse bias, A. Diode with beveled edge, B. Close-up view of edge, showing reduction of depletion region near the level, C. Guard ring. Figure 525 AP plus at N plus junction diode, A. Device configuration, B. Zero bias condition, C. Reverse bias to punch through. A short, lightly doped center region can also lead to punch through under reverse bias, as in Fig 525c. The mounting of a rectifier junction is critical to its ability to handle power. For diodes used in low-power circuits, glass or plastic encapsulation or a simple header mounting is adequate. However, high-current devices that must dissipate large amounts of heat require special mountings to transfer thermal energy away from the junction. A typical silicon power rectifier is mounted on a molybdenum or tungsten disc to match the thermal expansion properties of the SI. This disc is fastened to a large stud of copper or other thermally conductive material that can be bolted to a heat sink with appropriate cooling. The breakdown diode. As we discussed earlier in this section, the reverse bias breakdown voltage of a junction can be varied by choice of junction doping concentrations. The breakdown mechanism is the Zener effect, tunneling, for abrupt junctions. With extremely heavy doping, however, the more common breakdown is avalanche, impact ionization, typical of more lightly doped or graded junctions. By varying the doping we can fabricate diodes with specific breakdown. Voltages ranging from less than 1 volt to several hundred volts. If the junction is well designed, the breakdown will be sharp and the current after breakdown will be essentially independent of voltage, Fig 526a. When a diode is designed for a specific breakdown voltage, it is called a breakdown diode. Such diodes are also called Zener diodes, despite the fact that the actual breakdown mechanism is usually the avalanche effect. This error in terminology is due to an early mistake in identifying the first observations of breakdown in p-n junctions. Breakdown diodes can be used as voltage regulators in circuits with varying inputs. The 15V breakdown diode of Fig 526 holds the circuit output voltage V0 constant at 15V, while the input varies at voltages greater than 15V. For example, if versus is a rectified and filtered signal composed of a 17V DC component and a 1V ripple variation above and below 17V, the output V0 will remain constant at 15V. More complicated voltage regulator circuits can be designed using breakdown diodes, depending on the type of signal being regulated and the nature of the output load. In a similar application, such a device can be used as a reference diode. Since the breakdown voltage of a particular diode is known, the voltage across it during breakdown can be used as a reference in circuits that require a known value of voltage. Figure 526a breakdown diode, A. Current voltage characteristic, B. Application as a voltage regulator. We have considered the properties of p-n junctions under equilibrium conditions and with steady-state current flow. Most of the basic concepts of junction devices can be obtained from these properties, except for the important behavior of junctions under transient or AC conditions. Since most solid-state devices are used for switching or for processing AC signals, we cannot claim to understand p-n junctions without knowing at least the basics of time-dependent processes. Unfortunately, a complete analysis of these effects involves more mathematical manipulation than is appropriate for an introductory discussion. Basically, the problem involves solving the various current flow equations in two simultaneous variables, space and time. We can, however, obtain the basic results for several special cases which represent typical time-dependent applications of junction devices. In this section we investigate the important influence of excess carriers in transient and AC problems. The switching of a diode from its forward state to its reverse state is analyzed to illustrate a typical transient problem. Finally, these concepts are applied to the case of small AC signals to determine the equivalent capacitance of a p-n junction. Time variation of stored charge. Another look at the excess carrier distributions of a p-n junction under bias, for example, Fig 515, tells us that any change in current must lead to a change of charge stored in the carrier distributions. Since time is required in building up or depleting a charge distribution, however, the stored charge must inevitably lag behind the current in a time-dependent problem. This is inherently a capacitive effect, as we shall see in section 5.5.4. For a proper solution of a transient problem, we must use the time-dependent continuity equations, EQs. 431. We can obtain each component of the current at position x and time t from these equations, for example, from EQ. 431a, we can write. To obtain the instantaneous current density, we can integrate both sides at time t to obtain. For injection into a long n region from a p plus region, we can take the current at xn equals 0 to be all whole current, and jpat xn equal to be 0. Then the total injected current, including time variations, is. This result indicates that the whole current injected across the p plus, n junction, and therefore approximately the total diode current, is determined by two charge storage effects, 1, the usual recombination term Qp/Tp in which the excess carrier distribution is replaced every Tp seconds, and 2. A charge buildup, or depletion, term dQp/dt, which allows for the fact that the distribution of excess carriers can be increasing or decreasing in a time-dependent problem. For steady state the dQp/dt term is 0, and EQ 547 reduces to EQ 540, as expected. In fact, we could have written EQ 547 intuitively rather than having obtained it from the continuity equation, since it is reasonable that the whole current injected at any given time must supply minority carriers for recombination and for whatever variations that occur in the total stored charge. We can solve for the stored charge as a function of time for a given current transient. For example, the step turn-off transient, Fig 527a, in which a current I is suddenly removed at t equals 0, leaves the diode with stored charge. Since the excess holes in the N region must die out by recombination with the matching excess electron population, some time is required for Qp, t, to reach 0. Solving EQ 547, with Laplace transforms, with I, t70, equals 0 and Qp, 0, equal IVP, we obtain. Figure 527 effects of a step turn-off transient in a P+, N diode, A, current through the diode, B, decay of stored charge in the N region, C, excess hole distribution in the N region as a function of time during the transient. As expected, the stored charge dies out exponentially from its initial value IVP with a time constant equal to the whole lifetime in the N material. An important implication of Fig 527 is that even though the current is suddenly terminated, the voltage across the junction persists until Qp disappears. Since the excess hole concentration can be related to junction voltage by formulas derived in section 5.3.2, we can presumably solve for V, T. We already know that at any time during the transient, the excess hole concentration at xn equals 0 is. So that finding Pn, T, will easily give us the transient voltage. Unfortunately, it is not simple to obtain Pn, T, exactly from our expression for Qp, T. The problem is that the whole distribution does not remain in the convenient exponential form it has in steady state. As Fig 527c suggests, the quantity dP, xn, t, becomes markedly non-exponential as the transient proceeds. For example, since the injected hole current is proportional to the gradient of the hole distribution at xn equals 0, Fig 516a, 0 current implies 0 gradient. Thus the slope of the distribution must be exactly 0 at xn equals 0 throughout the transient 13. This 0 slope at the point of injection distorts the exponential distribution, particularly in the region near the junction. As time progresses in Fig 527c, dP, and therefore dN, decreases as the excess electrons and holes recombine. To find the exact expression for dP, xn, t, during the transient would require a rather difficult solution of the time-dependent continuity equation. An approximate solution for V, T, can be obtained by assuming an exponential distribution for dP at every instant during the decay. This type of quasi-steady state approximation neglects distortion due to the slope requirement at xn equals 0 and the effects of diffusion during the transient. Thus we would expect the calculation to give rather crude results. On the other hand, such a solution can give us a feeling for the variation of junction voltage during the transient. If we have for the stored charge at any instant relating Pn, T, to V, T, by EQ 549, we have. Thus in the quasi-steady state approximation, the junction voltage varies according to during the turn-off transient of Fig 527. This analysis, while not accurate in its details, does indicate clearly that the voltage across a PN junction cannot be changed instantaneously, and that stored charge can present a problem in a diode intended for switching applications. Many of the problems of stored charge can be reduced by designing a P+ N diode, for example, with a very narrow N region. If the N region is shorter than a hole diffusion length, very little charge is stored. Thus, little time is required to switch the diode on and off. This type of structure, called the narrow base diode, is considered in Prop 5.40. The switching process can be made still faster by purposely adding recombination centers, such as gold atoms in silicon, to increase the recombination rate. Reverse recovery transient. In most switching applications, a diode is switched from forward conduction to a reverse biased state, and vice versa. The resulting stored charge transient is somewhat more complicated than for a simple turn-off transient, and therefore it requires slightly more analysis. An important result of this example is that a reverse current much larger than the normal reverse saturation current can flow in a junction during the time required for readjustment of the stored charge. Let us assume a P+ N junction is driven by a square wave generator that periodically switches from plus E to E volts, Fig 528a. While E is positive, the diode is forward biased, and in steady state the current if flows through the junction. If E is much larger than the small forward voltage of the junction, the source voltage appears almost entirely across the resistor, and the current is approximately I equal if ER. After the generator voltage is reversed, T70, the current must initially reverse to I equal IR, ER. The reason for this unusually large reverse current through the diode is that the stored charge, and hence the junction voltage, cannot be changed instantaneously. Therefore, just as the current is reversed, the junction voltage remains at the small forward bias value it had before T equals 0. A voltage loop equation then tells us that the large reverse current, ER, must flow temporarily. While the current is negative through the junction, the slope of the dp, xn, distribution must be positive at xn equals 0. Figure 528 storage delay time in a P+ N diode, A, circuit and input square wave, B, hole distribution in the N region as a function of time during the transient, C, variation of current and voltage with time, D, sketch of transient current and voltage on the device's current voltage characteristic. As the stored charge is depleted from the neighborhood of the junction, Fig 528b, we can find the junction voltage again from EQ. 549. As long as Pn is positive, the junction voltage V, T, is positive and small, thus I, ER until Pn goes to 0. When the stored charge is depleted and Pn becomes negative, the junction exhibits a negative voltage. Since the reverse bias voltage of a junction can be large, the source voltage begins to divide between R and the junction. As time proceeds, the magnitude of the reverse current becomes smaller as more of E appears across the reverse junction, until finally the only current is the small reverse saturation current, which is characteristic of the diode. The time TSD required for the stored charge, and therefore the junction voltage, to become 0 is called the storage delay time. This delay time is an important figure of merit in evaluating diodes for switching applications. It is usually desirable that TSD be small compared with the switching times required, Fig 529. The critical parameter determining TSD is the carrier lifetime, TP, for the example of the P+ N junction. Since the recombination rate determines the speed with which excess holes can disappear from the N region, we would expect TSD to be proportional to TP. In fact, an exact analysis of the problem of Fig 528 leads to the result where the error function, ERF, is a tabulated function. Although the exact solution leading to EQ 554 is too lengthy for us to consider here, an approximate result can be obtained from the quasi-steady state assumption. Assume a P+ N diode is biased in the forward direction, with a current if at time t equals 0 the current is switched to IR. Use the appropriate boundary conditions to solve EQ 547. For Qp, T. Apply the quasi-steady state approximation to find the storage delay time TSD. Using Laplace transforms. Assuming that this is set to equal 0 when t equal TSD, and we obtain an important result of EQ 554, is that Tp can be calculated in a straightforward way from a measurement of storage delay time. In fact, measurement of TSD from an experimental arrangement such as Fig 528 is a common method of measuring lifetimes. In some cases this is a more convenient technique than the photoconductive decay measurement discussed in section 4.3.2. As in the case of the turn-off transient of the previous section, the storage delay time can be reduced by introducing recombination centers into the diode material, thus reducing the carrier lifetimes, or by utilizing the narrow base diode configuration. Switching diodes. In discussing rectifiers, we emphasized the importance of minimizing the reverse bias current and the power losses under forward bias. In many applications, time response can be important as well. If a junction diode is to be used to switch rapidly from the conducting to the non-conducting state and back again, special consideration must be given to its charge control properties. We have discussed the equations governing the turn-on time and the reverse recovery time of a junction. From EQs 547 and 554, it is clear that a diode with fast switching properties must either store very little charge in the neutral regions for steady forward currents or have a very short carrier lifetime, or both. As mentioned above, we can improve the switching speed of a diode by adding efficient recombination centers to the bulk material. For silicon diodes, gold doping is useful for this purpose. To a good approximation, the carrier lifetime varies with the reciprocal of the recombination center concentration. Thus, for example, a P+ N silicon diode may have Vp equal 1 microsecond and a reverse recovery time of 0.1 microsecond before gold doping. If the addition of 100 trillions gold atoms per cubic centimeter reduces the lifetime to 0.1 microseconds and TSD to 0.01 microseconds, 200 trillions per cubic centimeter gold atoms could reduce Vp to 0.01 microseconds and TSD to 1 nanoseconds, 10 to 9s. This process cannot be continued indefinitely, however. The reverse current due to generation of carriers from the O centers in the depletion region becomes appreciable with large O concentration, section 5.6.2. In addition, as the gold concentration approaches the lightest doping of the junction, the equilibrium carrier concentration of that region can be affected. A second approach to improving the diode switching time is to make the lightly doped neutral region shorter than a minority carrier diffusion length. This is the narrow base diode, Prob 5.40. In this case, the stored charge for forward conduction is very small, since most of the injected carriers diffuse through the lightly doped region to the end contact. When such a diode is switched to reverse conduction, very little time is required to eliminate the stored charge in the narrow neutral region. The mathematics involved in Prob 5.40 is particularly interesting, because it closely resembles the calculations we shall make in analyzing the bipolar junction transistor in Chapter 7. Capacitance of p-n junctions. There are basically two types of capacitance associated with a junction: 1, the junction capacitance due to the dipole in the transition region, and 2, the charge storage capacitance arising from the lagging behind of voltage. As current changes, due to charge storage effects 14, both of these capacitances are important, and they must be considered in designing p-n junction devices for use with time-varying signals. The junction capacitance, 1, is dominant under reverse bias conditions, and the charge storage capacitance, 2, is dominant when the junction is forward biased. In many applications of p-n junctions, the capacitance is a limiting factor in the usefulness of the device. On the other hand, there are important applications in which the capacitance discussed here can be useful in circuit applications and in providing important information about the structure of the p-n junction. The junction capacitance of a diode is easy to visualize from the charge distribution in the transition region, Fig 512. The uncompensated acceptor ions on the p side provide a negative charge, and an equal positive charge results from the ionized donors on the n side of the transition region. The capacitance of the resulting dipole is slightly more difficult to calculate than is the usual parallel plate capacitance, but we can obtain it in a few steps. Instead of the common expression C equal QV, which applies to capacitors in which charge is a linear function of voltage, we must use the more general definition. Since the charge Q on each side of the transition region varies nonlinearly with the applied voltage, Fig 530a, we can demonstrate this nonlinear dependence by reviewing the equations for the width of the transition region, W, and the resulting charge. The equilibrium value of W was found in EQ 521 to be. Since we are dealing with the non-equilibrium case with voltage V applied, we must use the altered value of the electrostatic potential barrier, V0, V, as discussed in relation to Fig 513. The proper expression for the width of the transition region is then. In this expression the applied voltage V can be either positive or negative to account for forward or reverse bias. As expected, the width of the transition region is increased for reverse bias and is decreased under forward bias. Figure 530. Depletion capacitance of a junction, A, P+, N junction showing variation of depletion edge on N side with reverse bias. Electrically, the structure looks like a parallel plate capacitor whose dielectric is the depletion region, and the plates are the space charge neutral regions, B, variation of depletion capacitance with reverse bias EQ. 563. We neglect XP0 in the heavily doped P+ material. Since the uncompensated charge Q on each side of the junction varies with the transition region width, variations in the applied voltage result in corresponding variations in the charge, as required for a capacitor. The value of Q can be written in terms of the doping concentration and transition region width on each side of the junction, Fig 512. Relating the total width of the transition region W to the individual widths XN0 and XP0 from EQs. 523, we have. And therefore the charge on each side of the dipole is. Thus the charge is indeed a nonlinear function of applied voltage. From this expression and the definition of capacitance in EQ 555, we can calculate the junction capacitance Cj. Since the voltage that varies the charge in the transition region is the barrier height, V0, V, we must take the derivative with respect to this potential difference. The quantity Cj is a voltage variable capacitance, since Cj is proportional to V0, V, 1 greater than 2. There are several important applications for variable capacitors, including use in tuned circuits. The PN junction device which makes use of the voltage variable properties of Cj is called a varactor. We shall discuss this device further in section 5.5.5. Although the dipole charge is distributed in the transition region of the junction, the form of the parallel plate capacitor formula is obtained from the expressions for Cj and W, Fig 530a. In analogy with the parallel plate capacitor, the transition region width W corresponds with the plate separation of the conventional capacitor. In the case of an asymmetrically doped junction, the transition region extends primarily into the less heavily doped side, and the capacitance is determined by only one of the doping concentrations, Fig 530a. For a P+, N junction, acceptors W donors and XN0W, while XP0 is negligible. The capacitance is then, Fig 530b. It is therefore possible to obtain the doping concentration of the lightly doped N region from a measurement of capacitance. For example, in a reverse biased junction the applied voltage V equal, VR can be made much larger than the contact potential V0, so that the latter becomes negligible. If the area of the junction can be measured, a reliable value of donors results from a measurement of Cj. However, these equations were obtained by assuming a sharp step junction. Certain modifications must be made in the case of a graded junction, Section 5.6.4 and Prop 5.42. The junction capacitance dominates the reactance of a PN junction under reverse bias. For forward bias, however, the charge storage, or diffusion capacitance, cesium becomes dominant. It has been recently SHOWN15 that the various time-dependent current components, as well as the boundary conditions, affect the diffusion capacitance in forward bias. We need to specify at which terminals the stored charges are extracted or reclaimed and where the relevant voltage drops occur. For long diodes whose dimensions are larger than the diffusion lengths, there is no diffusion capacitance. For a short diode, the reclaimable charge is 2/3 of the total stored charge. The diffusion capacitance due to stored holes on the N side of length C is. There is a similar contribution from the stored electrons on the P side, Fig 531. In practice, most silicon PN junctions behave like short diodes, while laser diodes made in direct bandgap, short lifetime, semiconductors often correspond to the long diode case. Similarly, we can determine the AC conductance by allowing small changes in the current. For example, for a long diode, we get. For the diode of example 5.4, what is the total depletion capacitance at 4 volts? The varactor diode. The term varactor is a shortened form of variable reactor, referring to the voltage variable capacitance of a reverse-biased PN junction. The equations derived in section 5.5.4 indicate that junction capacitance depends on the applied voltage and the design of the junction. In some cases, a junction with fixed reverse bias may be used as a capacitance of a set value. More commonly, the varactor diode is designed to exploit the voltage variable properties of the junction capacitance. For example, a varactor, or a set of varactors, may be used in the tuning stage of a radio receiver to replace the bulky variable plate capacitor. The size of the resulting circuit can be greatly reduced, and its dependability is improved. Other applications of varactors include use in harmonic generation, microwave frequency multiplication, and active filters. If the PN junction is abrupt, the capacitance varies as the square root of the reverse bias VREQ. 561. In a graded junction, however, the capacitance can usually be written in the form. For example, in a linearly graded junction the exponent n is 1/3, Prop 5.42. Thus the voltage sensitivity of Cj is greater for an abrupt junction than for a linearly graded junction. For this reason, varactor diodes are often made by epitaxial growth techniques, or by ion implantation. The epitaxial layer and the substrate doping profile can be designed to obtain junctions for which the exponent n in EQ 566 is greater than 1/2. Such junctions are called hyperabrupt junctions. In the set of doping profiles shown in Fig 532, the junction is assumed P+, and so that the depletion layer width W extends primarily into the N side. 3 types of doping profiles on the N side are illustrated, with the donor distribution d, x, given by Gxm, where G is a constant and the exponent m is 0, 1, or 3, 2. We can show, Prop 5.42, that the exponent n in EQ 566 is 1/m+2, for the P+ N junction. Thus for the profiles of Fig 532, n is 1/2 for the abrupt junction and 1/3 for the linearly graded junction. The hyperabrupt junction 16 with m equal 3/2 is particularly interesting for certain varactor applications, since for this case n equal 2 and the capacitance is proportional to Vr, 2. When such a capacitor is used with an inductor L in a resonant circuit, the resonant frequency varies linearly with the voltage applied to the varactor. Figure 532 graded junction profiles, linearly graded, abrupt, hyperabrupt. Because of the wide variety of Cj versus Vr dependencies available by choosing doping profiles, varactor diodes can be designed for specific applications. For some high-frequency applications, varactors can be designed to exploit the forward bias charge storage capacitance in short diodes. The approach we have taken in studying p-n junctions has focused on the basic principles of operation, neglecting secondary effects. This allows for a relatively uncluttered view of carrier injection and other junction properties, and illuminates the essential features of diode operation. To complete the description, however, we must now fill in a few details which can affect the operation of junction devices under special circumstances. Most of the deviations from the simple theory can be treated by fairly straightforward modifications of the basic equations. In this section we shall investigate the most important deviations and alter the theory wherever possible. In a few cases, we shall simply indicate the approach to be taken and the result. The most important alterations to the simple diode theory are the effects of contact potential and changes in majority carrier concentration on carrier injection, recombination and generation within the transition region, ohmic effects, and the effects of graded junctions. Effects of contact potential on carrier injection. If the forward bias IV characteristics of various semiconductor diodes are compared, it becomes clear that the band gap has an important influence on carrier injection. For example, Fig 533 compares the low temperature characteristics of heavily doped diodes having various band gaps. One obvious feature of this figure is that the current voltage characteristics appear square, that is, the current is very small until a critical forward bias is reached, and then the current increases rapidly. This is typical of exponentials plotted on such a scale. However, it is significant that the limiting voltage is slightly less than the value of the band gap in electron volts. The reason for the small current at low voltages for these devices can be understood from a simple rearrangement of the diode equation. If we rewrite EQ 536, for a forward-biased P+N diode, with V/Q, and include the exponential form for the minority carrier concentration Pn, we obtain hole injection into the N material is small if the forward bias V is much less than EFN, AVN, Q. For a P+N diode, this quantity is essentially the contact potential, since the Fermi level is near the valence band on the P side. If the N region is also heavily doped, the contact potential is almost equal to the band gap, Fig 534. This accounts for the dramatic increase in diode current near the band gap voltage in Fig 533. Contributing to the small current at lower voltages is the fact that the minority carrier concentration Pn equal N2I donors is very small at low temperature, Ni small, and with heavy doping, donors large. Figure 533 current voltage characteristics of heavily doped p-n junction diodes at 77 K, illustrating the effects of contact potential on the forward current. A. Germanium, e.g. M0.7 electron volts, B. Silicon, e.g. M1.1 electron volts, C. Gallium arsenide, e.g. M1.4 electron volts, D. Gallium arsenide phosphide, e.g. M1.9 electron volts. Figure 534 examples of contact potential for a heavily doped p-n junction, A. At equilibrium, B. Approaching the maximum forward bias V equal V0. The limiting forward bias across a p-n junction is equal to the contact potential, as in Fig 534b. This effect is not predicted by the simple diode equation, for which the current increases exponentially with applied voltage. The reason this important result is excluded in the simple theory is that in EQ 528, we neglect changes in the majority carrier concentrations on either side of the junction. This assumption is valid only for low injection levels. For large injected carrier concentrations, the excess majority carriers become important compared with the majority doping. For example, at low injection electron concentration equal hole concentration is important compared with the equilibrium minority electron concentration NP, but is negligible compared with the majority hole concentration. This was the basis for neglecting hole concentration in EQ 528. For high injection levels, however, hole concentration can be comparable to hole concentration, and we must write EQ 527 in the form From EQ 538, we get at either edge of the depletion region. For example, at SPO we then get, keeping in mind that hole concentration equal electron concentration, NPV/NP, and in high-level injection hole concentration 6 hole concentration, we approximately get. The rest of the derivation is very similar to that in section 5.3.2. Hence, the diode current in high-level injection scales as recombination and generation in the transition region. In analyzing the p-n junction, we have assumed that recombination and thermal generation of carriers occur primarily in the neutral p and n regions, outside the transition region. In this model, forward current in the diode is carried by recombination of excess minority carriers injected into each neutral region by the junction. Similarly, the reverse saturation current is due to the thermal generation of electron-hole pairs in the neutral regions and the subsequent diffusion of the generated minority carriers to the transition region, where they are swept to the other side by the field. In many devices this model is adequate. However, a more complete description of junction operation should include recombination and generation within the transition region itself. When a junction is forward biased, the transition region contains excess carriers of both types, which are in transit from one side of the junction to the other. Unless the width of the transition region W is very small compared with the carrier diffusion lengths Ln and Lp, significant recombination can take place within W. An accurate calculation of this recombination current is complicated by the fact that the recombination rate, which depends on the carrier concentrations EQ 4-5, varies with position within the transition region. Analysis of the recombination kinetics shows that the current due to recombination within W is proportional to Ni and increases with forward bias according to approximately exp. QV2 ∗. On the other hand, current due to recombination in the neutral regions is proportional to Pn and Np. EQ 536, and therefore to N2I donors and N2I acceptors, and increases according to exp. QV ∗. The diode equation can be modified to include this effect by including the parameter n, where n varies between 1 and 2, depending on the material and temperature. Since n determines the departure from the ideal diode characteristic, it is often called the ideality factor. The ratio of the two currents I, recombination in neutral regions, I, recombination in transition region, becomes small for wide bandgap materials, low temperatures, small Ni, and for low voltage. Thus the forward current for low injection in a silicon diode is likely to be dominated by recombination in the transition region, while a germanium diode may follow the usual diode equation. In either case, injection through W into the neutral regions becomes more important with increased voltage. Therefore, N in EQ 574 may vary from 2 at low voltage to 1 at higher voltage. Just as recombination within W can affect the forward characteristics, the reverse current through a junction can be influenced by carrier generation in the transition region. We found in section 5.3.3 that the reverse saturation current can be accounted for by the thermal generation of electron-hole pairs within a diffusion length of either side of the transition region. The generated minority carriers diffuse to the transition region, where they are swept to the other side of the junction by the electric field, Fig 535. However, carrier generation can take place within the transition region itself. If W is small compared with Ln or Lp, band-to-band generation of electron-hole pairs within the transition region is not important compared with generation in the neutral regions. However, the lack of free carriers within the space charge of the transition region can create a current due to the net generation of carriers by emission from recombination centers. Of the 4 generation recombination processes depicted in Fig 536, the 2 capture rates Rn and Rp are negligible within W because of the very small carrier concentrations in the reverse bias space charge region. Therefore, a recombination level ER near the center of the band gap can provide carriers through the thermal generation rates Gn and Gp. Each recombination center alternately emits an electron and a hole. Physically, This means that an electron at ER is thermally excited to the conduction band, Gn, and a valence band electron is subsequently excited thermally to the empty state on the recombination level, leaving a hole behind in the valence band, Gp. The process can then be repeated over and over, providing electrons for the conduction band and holes for the valence band. Normally, these emission processes are exactly balanced by the corresponding capture processes Rn and Rp. However, in the reverse bias transition region, generated carriers are swept out before recombination can occur, and net generation results. Figure 535 current in a reverse biased p-n junction due to thermal generation of carriers by a. band-to-band electron-hole pairs generation, and b. generation from a recombination level. Figure 536 capture and generation of carriers at a recombination center, a. capture and generation of electrons and holes, b. hole capture and generation processes redrawn in terms of valence band electron excitation to E. R, hole generation, and electron de-excitation from ER to EV, hole capture by ER. Of course, the importance of thermal generation within W depends on the temperature and the nature of the recombination centers. A level near the middle of the band gap is most effective, since for such centers neither Gn nor Gp requires thermal excitation of an electron over more than about half the band gap. If no recombination level is available, this type of generation is negligible. However, in most materials recombination centers exist near the middle of the gap due to trace impurities or lattice defects. Generation from centers within W is most important in materials with large band gaps, for which band-to-band generation in the neutral regions is small. Thus for silicon, generation within W is generally more important than for a narrower bandgap material such as germanium. The saturation current due to generation in the neutral regions was found to be essentially independent of reverse bias. However, generation within W naturally increases as W increases with reverse bias. Seen a result, the reverse current can increase almost linearly with W, or with the square root of reverse bias voltage. Ohmic losses. In deriving the diode equation we assumed that the voltage applied to the device appears entirely across the junction. Thus we neglected any voltage drop in the neutral regions or at the external contacts. For most devices this is a valid assumption, the doping is usually fairly high, so that the resistivity of each neutral region is low, and the area of a typical diode is large compared with its length. However, some devices do exhibit ohmic effects, which cause significant deviation from the expected current voltage characteristic. We can seldom represent ohmic losses in a diode accurately by including a simple resistance in series with the junction. The effects of voltage drops outside the transition region are complicated by the fact that the voltage drop depends on the current, which in turn is dictated by the voltage across the junction. For example, if we represent the series resistance of the P and N regions by Rp and Rn, respectively, we can write the junction voltage V as where Va is the external voltage applied to the device. As the current increases, there is an increasing voltage drop in Rp and Rn, and the junction voltage V decreases. This reduction in V lowers the level of injection so that the current increases more slowly with increased bias. A further complication in calculating the ohmic loss is that the conductivity of each neutral region increases with increasing carrier injection. Since the effects of EQ 576 are most pronounced at high injection levels, this conductivity modulation by the injected excess carriers can reduce Rp and Rn significantly. Ohmic losses are purposely avoided in properly designed devices by appropriate choices of doping and geometry. Therefore, deviations of the current generally appear only for very high currents, outside the normal operating range of the device. Figure 537 shows the forward and reverse current voltage characteristics of a p-n junction on a semi-log scale, both for an ideal Shockley diode as well as for non-ideal devices. For an ideal forward biased diode, we get a straight line on a semi-log plot reflecting the exponential dependence of current on voltage. On the other hand, taking into account all the second-order effects discussed in section 5.6, we see various regions of operation. At low current levels, we see the enhanced generation recombination current, leading to a higher diode ideality factor, N equal to. For moderate currents, we get ideal low-level injection and diffusion limited current, N equal 1. At higher currents, we get high-level injection and N equal 2, while at even higher currents, the ohmic drops in the space charge neutral regions become important. Similarly, in reverse bias, in an ideal diode, we have a constant, voltage-independent reverse saturation current. However, in actuality, we get an enhanced, voltage-dependent generation recombination leakage current. At very high reverse biases, the diode breaks down reversibly due to avalanche or Zener effects. Graded junctions. While the abrupt junction approximation accurately describes the properties of many epitaxially grown junctions, it is often inadequate in analyzing diffused or implanted junction devices. For shallow diffusions, in which the diffused impurity profile is very steep, Fig 538a, the abrupt approximation is usually acceptable. If the impurity profile is spread out into the sample, however, a graded junction can result, Fig 538b. Several of the expressions we have derived for the abrupt junction must be modified for this case, see section 5.5.5. The graded junction problem can be solved analytically if, for example, we make a linear approximation of the net impurity distribution near the junction, Fig 538c. Figure 537 forward and reverse current voltage characteristics plotted on semi-log scales, with current normalized with respect to saturation current, I0, A. The ideal forward characteristic is an exponential with an ideality factor n equal 1, dashed straight line on log linear plot. The actual forward characteristics of a typical diode, solid line, have four regimes of operation. B. Ideal reverse characteristic, dashed line, is a voltage-independent current equal, I0. Actual leakage characteristics, solid line, are higher due to generation in the depletion region, and also show breakdown at high voltages. We assume that the graded region can be described approximately by where G is a grade constant giving the slope of the net impurity distribution. In Poisson's equation EQ 514, the linear approximation becomes within the transition region. In this approximation we assume complete ionization of the impurities and neglect the carrier concentrations in the transition region, as before. The net space charge varies linearly over W, and the electric field distribution is therefore parabolic. The expressions for contact potential and junction capacitance are different from the abrupt junction case, Fig 539 and Prob 5.42, since the electric field is no longer linear on each side of the junction. Figure 538 approximations to diffused junctions, A. Shallow diffusion, abrupt, B. Deep drive-in diffusion with source removed, graded, C. Linear approximation to the graded junction. In a graded junction the usual depletion approximation is often inaccurate. If the grade constant G is small, the carrier concentrations, Pn, can be important in EQ 578. Similarly, the usual assumption of negligible space charge outside the transition region is questionable for small g. It would be more accurate to refer to the regions just outside the transition region as quasi-neutral rather than neutral. Thus the edges of the transition region are not sharp as Fig 539 implies but are spread out in X. These effects complicate calculations of junction properties, and a computer must be used in solving the problem accurately. Most of the conclusions we have made regarding carrier injection, recombination and generation currents, and other properties are qualitatively applicable to graded junctions, with some alterations in the functional form of the resulting equations. Therefore, we can apply most of our basic concepts of junction theory to reasonably graded junctions as long as we remember that certain modifications should be made in accurate computations. Figure 539 Properties of the graded junction transition region. A. Net impurity profile. B. Net charge distribution. C. Electric field. D. Electrostatic potential. Many of the useful properties of a p-n junction can be achieved by simply forming an appropriate metal semiconductor contact. This approach is obviously attractive because of its simplicity of fabrication, also, as we shall see. In this section, metal semiconductor junctions are particularly useful when high-speed rectification is required. On the other hand, we also must be able to form non-rectifying, ohmic, contacts to semiconductors. Therefore, this section deals with both rectifying and ohmic contacts. Schottky barriers. In section 2.2.1 we discuss the work function Qm of a metal in a vacuum. An energy of Qm is required to remove an electron at the Fermi level to the vacuum outside the metal. Typical values of M for very clean surfaces are 4.3 V for aluminum and 4.8 V for gold. When negative charges are brought near the metal surface, positive, image, charges are induced in the metal. When this image force is combined with an applied electric field, the effective work function is somewhat reduced. Such barrier lowering is called the Schottky effect, and this terminology is carried over to the discussion of potential barriers arising in metal semiconductor contacts. Although the Schottky effect is only a part of the explanation of metal semiconductor contacts, rectifying contacts are generally referred to as Schottky barrier diodes. In this section we shall see how such barriers arise in metal semiconductor contacts. First we consider barriers in ideal metal semiconductor junctions, and then in section 5.7.4 we will include effects which alter the barrier height. When a metal with work function Qm is brought in contact with a semiconductor having a work function Qs, charge transfer occurs until the Fermi levels align at equilibrium, Fig 540. For example, when M7s, the semiconductor Fermi level is initially higher than that of the metal before contact is made. To align the two Fermi levels, the electrostatic potential of the semiconductor must be raised, i.e., the electron energies must be lowered, relative to that of the metal. In the N-type semiconductor of Fig 540 a depletion region W is formed near the junction. The positive charge due to uncompensated donor ions within W matches the negative charge on the metal. The electric field and the bending of the bands within W are similar to effects already discussed for p-n junctions. For example, the depletion width W in the semiconductor can be calculated from EQ 521, by using the P plus N approximation, i.e., by assuming the negative charge in the dipole as a thin sheet of charge to the left of the junction. Similarly, the junction capacitance is APS/W, as in the P plus N junction 17. The equilibrium contact potential V0, which prevents further net electron diffusion from the semiconductor conduction band into the metal, is the difference in work function potentials M, S. The potential barrier height B for electron injection from the metal into the semiconductor conduction band is Mx, where Qx, called the electron affinity, is measured from the vacuum level to the semiconductor conduction band H. The equilibrium potential difference V0 can be decreased or increased by the application of either forward or reverse bias voltage, as in the p-n junction. Figure 541 illustrates a Schottky barrier on a p-type semiconductor, with M6s. In this case aligning the Fermi levels at equilibrium requires a positive charge on the metal side and a negative charge on the semiconductor side of the junction. The negative charge is accommodated by a depletion region W in which ionized acceptors are left uncompensated by holes. The potential barrier V0 retarding hole diffusion from the semiconductor to the metal is S, M, and as before this barrier can be raised or lowered by the application of voltage across the junction. In visualizing the barrier for holes, we recall from Fig 511 that the electrostatic potential barrier for positive charge is opposite to the barrier on the electron energy diagram. The two other cases of ideal metal semiconductor contacts, M6s for N-type semiconductors, and M7s for P-type, result in non-rectifying contacts. We will save treatment of these cases for section 5.7.3, where ohmic contacts are discussed. Figure 541. A Schottky barrier between a p-type semiconductor and a metal having a smaller work function. A. Band diagrams before joining. B. Band diagram for the junction at equilibrium. Rectifying contacts. When a forward bias voltage V is applied to the Schottky barrier of Fig 540b, the contact potential is reduced from V0 to V0, V, Fig 542a. As a result, electrons in the semiconductor conduction band can diffuse across the depletion region to the metal. This gives rise to a forward current, metal to semiconductor, through the junction. Conversely, a reverse bias increases the barrier to V0 plus Vr, and electron flow from semiconductor to metal becomes negligible. In either case, flow of electrons from the metal to the semiconductor is retarded by the barrier M, X. The resulting diode equation is similar in form to that of the p-n junction. I equal I0, EQV caret, 1, 579. As Fig 542c suggests. In this case, the reverse saturation current I0 is not simply derived as it was for the p-n junction. One important feature we can predict intuitively, however, is that the saturation current should depend upon the size of the barrier B for electron injection from the metal into the semiconductor. This barrier, which is M, X for the ideal case shown in Fig 542, is unaffected by the bias voltage. We expect the probability of an electron in the metal surmounting this barrier to be given by a Boltzmann factor. Thus, the diode equation, 579, applies also to the metal p-type semiconductor junction of Fig 541. In this case, forward voltage is defined with the semiconductor biased positively with respect to the metal. Forward current increases as this voltage lowers the potential barrier to V0, V, and holes flow from the semiconductor to the metal. Of course, a reverse voltage increases the barrier for hole flow and the current becomes negligible. In both of these cases, the Schottky barrier diode is rectifying, with easy current flow in the forward direction and little current in the reverse direction. We also note that the forward current in each case is due to the injection of majority carriers from the semiconductor into the metal. The absence of minority carrier injection and the associated storage delay time is an important feature of Schottky barrier diodes. Although some minority carrier injection occurs at high current levels, these are essentially majority carrier devices. Their high-frequency properties and switching speed are therefore generally better than typical p-n junctions. In the early days of semiconductor technology, rectifying contacts were made simply by pressing a wire against the surface of the semiconductor. In modern devices, however, the metal semiconductor contact is made by depositing an appropriate metal film on a clean semiconductor surface and defining the contact pattern photolithographically. Schottky barrier devices are particularly well suited for use in densely packed integrated circuits, because fewer photolithographic masking steps are required compared to p-n junction devices. Figure 542. Effects of forward and reverse bias on the junction of Fig 540, A. Forward bias, B. Reverse bias, C. Typical current voltage characteristic. Ohmic contacts. In many cases we wish to have an ohmic metal semiconductor contact, having a linear current voltage characteristic in both biasing directions. For example, the surface of a typical integrated circuit is a maze of P and N regions, which must be contacted and interconnected. It is important that such contacts be ohmic, with minimal resistance and no tendency to rectify signals. Ideal metal semiconductor contacts are ohmic when the charge induced in the semiconductor in aligning the Fermi levels is provided by majority carriers, Fig 543. For example, in the M6s, N-type, case of Fig 543a, the Fermi levels are aligned at equilibrium by transferring electrons from the metal to the semiconductor. This raises the semiconductor electron energies, lowers the electrostatic potential, relative to the metal at equilibrium, Fig 543b. In this case, the barrier to electron flow between the metal and the semiconductor is small and easily overcome by a small voltage. Similarly, the case M7s, p-type, results in easy hole flow across the junction, Fig 543d. Unlike the rectifying contacts discussed previously, no depletion region occurs in the semiconductor in these cases, since the electrostatic potential difference required to align the Fermi levels at equilibrium calls for accumulation of majority carriers in the semiconductor. A practical method for forming ohmic contacts is by doping the semiconductor heavily in the contact region. Thus, if a barrier exists at the interface, the depletion width is small enough to allow carriers to tunnel through the barrier. For example, gold containing a small percentage of antimony can be alloyed to N-type silicon, forming an N+ layer at the semiconductor surface and an excellent ohmic contact. Similarly, P-type material requires a P+ surface layer in contact with the metal. In the case of aluminum on P-type silicon, the metal contact also provides the acceptor dopant. Thus, the required P+ surface layer is formed during a brief heat treatment of the contact after the aluminum is deposited. Figure 543. Ohmic metal semiconductor contacts, A, M6s for an N-type semiconductor, and B, the equilibrium band diagram for the junction, C, M7s for a P-type semiconductor, and D, the junction at equilibrium. Typical Schottky barriers. The discussion of ideal metal semiconductor contacts does not include certain effects of the junction between the two dissimilar materials. Unlike a p-n junction, which occurs within a single crystal, a Schottky barrier junction includes a termination of the semiconductor crystal. The semiconductor surface contains surface states due to incomplete covalent bonds and other effects, which can lead to charges at the metal semiconductor interface. Furthermore, the contact is seldom an atomically sharp discontinuity between the semiconductor crystal and the metal. There is typically a thin interfacial layer, which is neither semiconductor nor metal. For example, silicon crystals are covered by a thin, 10 to 20 angstroms, oxide layer even after etching or cleaving in atmospheric conditions. Therefore, deposition of a metal on such a silicon surface leaves a glassy interfacial layer at the junction. Although electrons can tunnel through this thin layer, it does affect the barrier to current transport through the junction. Because of surface states, the interfacial layer, microscopic clusters of metal semiconductor phases, and other effects, it is difficult to fabricate junctions with barriers near the ideal values predicted from the work functions of the two isolated materials. Therefore, measured barrier heights are used in device design. In compound semiconductors, the interfacial layer introduces states in the semiconductor band gap that pin the Fermi level at a fixed position, regardless of the metal used, Fig 544. For example, a collection of interface states located 0.7–0.9 electron volts below the conduction band pins F at the surface of N-type gallium arsenide, and the Schottky barrier height is determined from this pinning effect rather than by the work function of the metal. An interesting case is N-type indium arsenide, Fig 544b, in which F at the interface is pinned above the conduction band H. As a result, ohmic contact to N-type ENAs can be made by depositing virtually any metal on the surface. For Si, good Schottky barriers are formed by various metals, such as gold or platinum. In the case of platinum, heat treatment results in a platinum silicide layer, which provides a reliable Schottky barrier with B. 0.85 V on N-type silicon. A full treatment of Schottky barrier diodes results in a forward current equation of the form where B is a constant containing parameters of the junction properties and N is a number between 1 and 2, similar to the ideality factor in EQ. 574, but arising from different reasons. The mathematics of this derivation is similar to that of thermionic emission, and the factor B corresponds to an effective Richardson constant in the thermionic problem. Figure 544. Fermi level pinning by interface states in compound semiconductors. A. F is pinned near EC, 0.8 electron volts in N-type gallium arsenide, regardless of the choice of metal. B. F is pinned above EC in N-type indium arsenide, providing an excellent ohmic contact. Thus far we have discussed p-n junctions formed within a single semiconductor, homojunctions, and junctions between a metal and a semiconductor. The third important class of junctions consist of those between two lattice-matched semiconductors with different band gaps, heterojunctions. We discussed lattice matching in section 1.4.1. The interface between two such semiconductors may be virtually free of defects, and continuous crystals containing single or multiple heterojunctions can be formed. The availability of heterojunctions and multi-layer structures in compound semiconductors opens a broad range of possibilities for device development. We will discuss many of these applications in later chapters, including heterojunction bipolar transistors, field effect transistors, and semiconductor lasers. When semiconductors of different band gaps, work functions, and electron affinities are brought together to form a junction, we expect discontinuities in the energy bands as the Fermi levels line up at equilibrium, Fig 545. The discontinuities in the conduction band EC and the valence band EV accommodate the difference in band gap between the two semiconductors, e.g. in an ideal case, EC would be the difference in electron affinities Q, X2, X1, and EV would be found from e.g. EC. This is known as the Anderson affinity rule. In practice, the band discontinuities are found experimentally for particular semiconductor pairs. For example, in the commonly used system gallium arsenide aluminum gallium arsenide, see Figs 3.6 and 3.13, the direct band gap difference, e.g. between the wider band gap aluminum gallium arsenide and the narrower band gap gallium arsenide, is apportioned approximately 2:3 in the conduction band and 1:3 in the valence band for the heterojunction. The built-in contact potential is divided between the two semiconductors as required to align the Fermi levels at equilibrium. The resulting depletion region on each side of the heterojunction and the amount of built-in potential on each side, making up the contact potential V0, are found by solving Poisson's equation with the boundary condition of continuous electric flux density, P11 equal P22, at the junction. The barrier that electrons must overcome in moving from the N side to the P side may be quite different from the barrier for holes moving from P to N. The depletion region on each side is analogous to that described in EQ 523, except that we must account for the different dielectric constants in the two semiconductors. Figure 545. An ideal heterojunction between a p-type, wide bandgap semiconductor and an n-type narrower bandgap semiconductor, A. Band diagrams before joining, B. Band discontinuities and band bending at equilibrium. To draw the band diagram for any semiconductor device involving homojunctions or heterojunctions, we need material parameters such as the band gap and the electron affinity, which depend on the semiconductor. Material but not on the doping, and the work function, which depends on the semiconductor as well as the doping. The electron affinity and work function are referenced to the vacuum level. The true vacuum level, or global vacuum level, EVAC, is the potential energy reference when an electron is taken out of the semiconductor to infinity, where it sees no forces. Hence, the true vacuum level is a constant, Fig 545. That introduces an apparent contradiction, however, because looking at the band bending in a semiconductor device, it seems to imply that the electron affinity in the semiconductor changes as a function of position, which is impossible because the electron affinity is a material parameter. Therefore, we need to introduce the new concept of the local vacuum level, EVAC, LOC, which varies along with and parallel to the conduction band edge, thereby keeping the electron affinity constant. The local vacuum level tracks the potential energy of an electron if it is moved just outside of the semiconductor, but not far away. The difference between the local and global vacuum levels is due to the electrical work done against the fringing electric fields of the depletion region, and is equal to the potential energy QV0 due to the built-in contact potential V0 in equilibrium. This potential energy can, of course, be modified by an applied bias. To draw the band diagram for a heterojunction accurately, we must not only use the proper values for the band discontinuities but also account for the band bending in the junction. To do this, we must solve Poisson's equation across the heterojunction, taking into account the details of doping and space charge, which generally requires a computer solution. We can, however, sketch an approximate diagram without a detailed calculation. Given the experimental band offsets EV and EC, we can proceed as follows. 1. Align the Fermi level with the two semiconductor bands separated. Leave space for the transition region. 2. The metallurgical junction, x equals 0, is located near the more heavily doped side. At x equals 0 put EV and EC, separated by the appropriate band gaps. 3. Connect the conduction band and valence band regions, keeping the band gap constant in each material. Steps 2 and 3 of this procedure are where the exact band bending is important and must be obtained by solving Poisson's equation. In step 2 we must use the band offset values EC and EV for the specific pair of semiconductors in the heterojunction. For heterojunctions in the gallium arsenide-aluminum gallium arsenide system, the direct band gap difference E G is accommodated approximately 2-3 in the conduction band and 1-3 in the valence band. For an aluminum composition of 0.3, the aluminum gallium arsenide is direct, see Fig 3.6, with E G equal 1.85 electron volts. Sketch the band diagrams for two heterojunction cases, N+, aluminum 0.3 gallium 0.7 arsenide on N-type gallium arsenide, and N+, aluminum 0.3 gallium 0.7 arsenide on P+, gallium arsenide 18. Taking Eg equal 1.85 to 1.43 equal 0.42 electron volts, the band offsets are Ec equal 0.28 electron volts and Ev equal 0.14 electron volts. In each case we draw the equilibrium Fermi level, add the appropriate bands far from the junction, add the band offsets while estimating the relative amounts of band bending and position of x equals 0 for the particular doping on the two sides, and finally sketch the band edges so that Eg is maintained in each separate semiconductor right up to the heterojunction at x equals 0. Taking Eg equal 1.85 to 1.43 equal 0.42 electron volts, the band offsets are Ec equal 0.28 eV and Ev equal 0.14 electron volts. In each case we draw the equilibrium Fermi level, add the appropriate bands far from the junction, add the band offsets while estimating the relative amounts of band bending and position of x equals 0 for the particular doping on the two sides, and finally sketch the band edges so that Eg is maintained in each separate semiconductor right up to the heterojunction at x equals 0. A particularly important example of a heterojunction is shown in Figure 546, in which heavily N-type aluminum gallium arsenide is grown on lightly doped gallium arsenide. In this example, the discontinuity in the conduction band allows electrons to spill over from the N+ aluminum gallium arsenide into the gallium arsenide, where they become trapped in the potential well. Arsenide a result, electrons collect on the gallium arsenide side of the heterojunction and move the Fermi level above the conduction band in the gallium arsenide near the interface. These electrons are confined in a narrow potential well in the gallium arsenide conduction band. If we construct a device in which conduction occurs parallel to the interface, the electrons in such a potential well form a two-dimensional electron gas with very interesting device properties. As we shall see in Chapter 6, electron conduction in such a potential well can result in very high mobility electrons. This high mobility is due to the fact that the electrons in this well come from the aluminum gallium arsenide, and not from doping in the gallium arsenide. Arsenide a result, there is negligible impurity scattering in the gallium arsenide well, and the mobility is controlled almost entirely by lattice scattering, phonons. At low temperatures, where phonon scattering is low, the mobility in this region can be very high. If the band bending in the gallium arsenide conduction band is strong enough, the potential well may be extremely narrow, so that discrete states such as E1 and E2 in Fig 546 are formed. We will return to this example in Chapter 6. Another obvious feature of Fig 546 is that the concept of a contact potential barrier QV0 for both electrons and holes in a homojunction is no longer valid for the heterojunction. In Fig 546 the barrier for electrons QVN is smaller than the barrier for holes QVP. This property of a heterojunction can be used to alter the relative injection of electrons and holes, as we shall see in section 7.9. 5.1 Diodes and other semiconductor devices are made by combinations of steps such as oxidation, selective doping, via implant or diffusion, and the deposition of various insulators or metals in concert with etching, using patterns formed by photolithography. 5.2 When we bring P and N-type semiconductors into contact to make a P-N junction diode, carriers diffuse across the junction until we get a flat Fermi level in equilibrium. A built-in junction potential barrier is formed between the P and N sides, which reflects the voltage drop across the depletion region. This is a dynamic equilibrium, in which there is a continual diffusion of electrons from the N to the P side, and holes from P to N, but at a reduced rate over the potential barrier, and these fluxes are cancelled by opposing flows of minority carriers diffusing to the depletion edges and getting swept across the junction. 5.3 The electrostatics of the depletion region are determined by solving the Poisson's equation. For uniformly doped abrupt step junctions we get linearly varying electric fields that are highest at the metallurgical junction. We get a wider depletion region on the more lightly doped side and equal and opposite depletion charges on the two sides of the junction. 5.4 For an ideal Shockley diode, one assumes negligible generation recombination inside the depletion region. In forward bias, the built-in potential barrier is lowered, making it exponentially easier for majority carriers to diffuse across. 5.5 The opposing minority carrier fluxes are unaffected because they are limited by how often the few minority carriers diffuse to the depletion edges. Far from the junction, the current is carried by drift of the majority carriers, which are injected across the junction to the other side, where, as minority carriers, they give rise to diffusion currents. 5.6 In reverse bias, for ideal diodes, the voltage-independent reverse current is due to the collection of thermally generated minority carriers on either side diffusing to the depletion region and then being swept across. The current flow from N to P is small and is the basis of diode rectifiers. 5.7 For high reverse biases, diodes undergo reversible breakdown due to quantum mechanical tunneling, Zener mechanism, across a narrow depletion region for very heavily doped junctions or due to impact ionization or avalanche multiplication of carriers in a wider depletion region for lightly doped junctions. For narrow diodes, there can also be punch-through from one contact to the other. 5.8 Varying the bias leads to diode switching. The diode transient behavior can be found by solving the continuity equation, for example, using Laplace transforms, with suitable initial and boundary conditions. 5.9 Small signal capacitance in a semiconductor device is caused by a change in the charge storage as a function of bias. There are two components of diode. Capacitance, depletion capacitance, due to exposed dopant charges in the depletion region, dominates in reverse bias, and diffusion capacitance, due to stored excess mobile carriers, dominates in forward bias. 5.10 Real diodes can deviate from Shockley ideal diodes, which have negligible generation recombination in the depletion region. Generation recombination in the depletion region increases the diode ideality factor N from 1 to 2 in forward bias and introduces a roughly square root voltage dependence of reverse leakage current. 5.11 High-level carrier injection for large forward bias, in which the injected minority carrier concentration is comparable to the background majority carrier concentration, also makes N equal to. Series resistance effects play a role as well for higher currents. 5.12 Graded junctions, where the doping concentrations on either side are not constant, are qualitatively similar to abrupt junctions, but are harder to analyze. They have different CV than abrupt junctions have. 5.13 Metal semiconductor junctions behave as Schottky diodes, if the Fermi level alignments are such that there is a depletion of majority carriers in the semiconductor, or ohmic contacts, if there is no depletion region formed in the semiconductor. 5.14 Junctions between dissimilar semiconductors are called heterojunctions. With respect to a vacuum reference level, one looks at the conduction band edges, electron affinities, and band gaps to determine the band offsets, and at the Fermi levels, work functions, to determine the direction of carrier transfer. Electrons flow from the high to low Fermi level regions, and holes flow the opposite way.